Welcome to the podcast series The New Student Pharmacist, where we discuss chemistry and pharmacy, as well as leaders in pharmacy careers, community, and chemistry and pharmacy research. We encourage you to support the work we are doing and follow us on Spotify and Apple Podcasts by subscribing for free. Note, the views on the podcast represent those of my guest and I.
Purpose of these episodes not at all for advice or medical suggestions. These are aimed to provide support to peer pharmacists in training in educational and intellectually stimulating ways. Again, these are not at all for medical advice or medical suggestions. Please see your local board and state-certified health professional. The views of this podcast represent those of my guests and I.
Good afternoon, students. It is so good to have you in General Chemistry 1 this afternoon. I am so excited. I am so thrilled. I am so honored, and I am so privileged to have you as my students this semester. As we will begin, I want to remind everyone that you are not alone. This is an academic community. Remember to get help when needed. Reach out to university services if needed. Never give up. Keep trying. We are here to help you be ethical, honest, intelligent, and successful scientists. However, at the end of the day, you must be responsible, ethical, and hardworking. As we begin, I always like to reflect on the work of Werner Heisenberg. You know, he was, during his postdoctoral assistantship with Niels Bohr, Heisenberg formulated his famous uncertainty principle. At the age of 25, he became the chair in theoretical physics at the University of Leipzig. At 32, he was one of the youngest scientists to receive the Nobel Prize. He lived from 1901 to 1976. So this will encourage and inspire you, hopefully, that it's possible, no matter how young you are. So, let's proceed. We're going to go straight to, I'd like to begin the lecture discussing the significance of DNA, so I'm just going to go ahead and talk about it. So, for DNA, we know that in this class I tend to ask you what functional groups do you see, what atoms do you see, and why is DNA important. Then we'll give you some time and we'll give you the opportunity to go through the structure and just think about those answers. Which atoms do you see? What functional groups do you see? And why is this molecule, this polymer, why is it important? Okay, so let's begin. So right now we see that we have nitrogen. We see that we have nitrogen. We have nitrogen. Let me see. There you go. We have nitrogen. Nitrogen. We also have wait a second, having a few technical difficulties, so let me see if I can adjust something quickly before I continue with the lecture for today. Adjust something quickly. Okay, let's proceed. So we have nitrogen, we have phosphorus, nitrogen, we have phosphorus, we also have hydrogen, we also have carbon, and we also have oxygen. Yeah, that covers basically all of them we have here: nitrogen, hydrogen, oxygen, phosphorus, and carbon. So those are the atoms that we see. The functional groups that we see, we have the amine. Is the amine there? Amine there. Right there. There we go. You have the amine there. See? There we go. And then we also have the phosphate there. And then we have other functional groups, but I'm not going into all that. We have hydroxyls there. And that's as far as I want to go with you today. So why is DNA important? DNA is important for several reasons. One, it plays a role in the replication of cells. It plays a role in maintenance and integrity of cellular function. DNA is important because mutations in DNA can cause diseases, can lead to downstream effects such as diseases. DNA is very, very important. It's like the information, the set of instructions, the blueprint for a specific cell. Not every gene is expressed in every cell, and that's a discussion for a different day. But gene expression is very dependent, heavily dependent on the genes, and genes are made up of DNA. So, very important biopolymer. So let me erase, and we'll proceed forward. Let's see. So yeah, DNA is very important. It contributed to a lot of discovery. You could go into all of the discussions as to whether it being semi-conservative in terms of its replication, all those things. But that's not for this class today. So let's talk about the goals and objectives of this class. I'd like to remind everyone of this because it's important for us to keep focus. The goal of the class is to teach the chemistry content in a way that is relevant to the Bahamian student and digestible for their understanding. The sequence is as follows. Understand the fundamental concept A. Practice problems relevant to understanding concept A. Learn more nuanced details about each concept, and practice more complex problems and integrate the details and the fundamental understanding. So today, we're actually going to go straight into our discussion for this lecture. This is previous ideas that we discussed earlier. There we go. So I've already gone through the discussion in which we drew resonance structures, drew different Lewis dot structures. One of the things I want to do today is I want to emphasize some key ideas associated with resonance and resonance structures. So the resonance hybrid is one of the best qualitative descriptors of the molecule, and it gives us an idea. It points to the fact that electrons are not in one position all the time. It gives us it's a better description, a better treatment of a better it leans closer and closer to a quantum mechanical treatment of molecular structure. It gives us an idea. It points to the fact that electrons are delocalized. It's a good structure, not perfect, but it's a good description. And one of the things I want to emphasize in this lecture today is I want us to look at the resonance structures of nitrate. And so look at the resonance structures of nitrate. So let me, right here, nitrate. So I want us to look at the resonance structures of, I'll be focused on today in terms of resonance structures, and then we'll proceed forward into molecular geometry, and we'll continue to discuss some more ideas in terms of molecular orbital theory and valence bond theory. So let me erase, and now let's proceed. There we go. So let's talk about nitrate. So nitrate, NO3 minus. So we know when we look at nitrate is in group 5. That's 5 valence electron. Oxygen is in group 6. So that's 6 valence electrons. So when we add those up, 18 plus 5 is 23. And then we consider the 1 that comes from the minus charge, so plus 1. And that gives us 24. That's that. So let's just so we have that in mind. So we're counting for 24 electrons. So let's come on this side right there, and let's draw out what we think the structure would look like. So we consider all of our electrons. We take our atom, we place it there, put single bonds between each atom. So NO, let me just try this a little bit better. Actually, I can do a little better than that. So let me erase. Let's erase that. There we go. And let's erase that. And let's do this. Like this. There we go. Okay, so that's that. We draw single bonds. So 24 minus 2, 4, 6. 24 minus 6 is 18. So we put 1, 2, 3, 4, 5. 2, 3, 4, 5. 2. And then, okay. So 6 dots around anything, and that accounts for all of the things. However, accounts for all of the electrons. However, the issue that we have here is that this has a minus charge, formal charge of -1. This has a formal charge of -1. This has a formal charge of -1, and this has a formal charge of +2. Though this is a resonance structure, it's not the best resonance structure we can draw, because one of the aims for drawing resonance structures is you want to make sure you follow the octet rule. That's a big chief idea. And you also want to make sure that you minimize formal charge. So that's one, but let's look at another one. So that's one we can draw. But let's look at another one. So look at another one. Okay, so this is a better one right here. This is right here. This is a good one right here. It has an overall charge of -1, and we've minimized formal charge as best as possible. Everything obeys the octet rule, so we've ticked all of the boxes. So this is a good structure right here. You notice that we were able to draw two structures. You can draw different structures in which you have. So say for example, just keep that structure in your mind. We can draw a structure where we have the double bond here. So that, and then we have a single bond here. And we have same nitrogen still has the same form of charge, but with double bonds change position. So as you can see, that's resonance structure, that's resonance structure, this is the resonance structure. There's several you can draw. However, the best structure is one that minimizes formal charge and obeys the octet rule. And you want to make sure you hit all of those criteria when you're drawing resonance structures. Now we can draw another one, which we have the double bond on the other oxygen. So there, there. Actually, let me not rush this. Let me take my time and draw this clearly. So there you have. There we go. There we go. There we go. There we go. That. There we go. So that's another resonance structure. So we just drew 4 structures for the same molecule, for the same polyatomic ion. We drew 4 different Lewis dot structures. Different in the sense that the positions of the electrons are the position of the electrons between each atom. It's a slightly different configuration, or slightly different arrangement. That's a better word to use. However, a slightly different position. That's a better word to use. But yeah, so we just drew several structures for nitrate. It's famous for its resonance, and let me just note something. When we're drawing different resonance structures, so say we have resonance structure A, resonance structure B, resonance structure C, there we go. So that's how you know you're drawing resonance structures, as opposed to, so the arrows, these are the arrows for resonance, and these are the arrows for equilibrium. I'm just knowing this because it's important to know the difference. So this is resonance, these are resonance arrows. When we're drawing resonance structures, these are the arrows we use when we're talking about equilibrium. So it's important to just note that difference. But I just wanted to show that to y'all, but let's move on. Let me just erase, guys, and then we're going to proceed forward. Sorry about the background noise. Yeah, let me just erase. So it's important key ideas that I want you to take away from this exercise. You can draw different Lewis dot structures for molecules that tend to have double bonds and single bonds in the same structure. And it's important for you to know that the best structure, or the best resonance structures you can draw, minimizes formal charge, and it also follows the octet rule. That's the big thing. The big idea is make sure it obeys the octet rule, especially for second group elements. second period elements, excuse me. Okay, so let's talk about, so this is just, another thing I want to do is, I want to make sure you understand how to study this type of material. Now, some people, when it comes to andragogy, or learning when it comes to adults, some people may promote, everyone learns differently, and you must just figure it out yourself. I'm going to show you how I study this material, how I go through material, and how am I able to understand it as your professor this semester. So I'm going to show you how I study this material. So we're going to discuss, say for example, so this is going to be a very engaging discussion this afternoon. Say for example, you were given a piece of a pamphlet, or you were given a section of a textbook, and I told you, I need you to study this quickly, study this in about 3 or 4 days, and I want you to come back and I'm going to assess you on this. Say you had a very specific reason to study. So we've established our goal, we've established our motivation. We want to understand rules for resonance forms, and that's the topic. And it has objectives, so we know what should be our what should be achieved, what should we aim for, what should we strive for as we are studying this material. We want to keep these things looming in our mind as to am I doing something that complements to me achieving these objectives. So the objectives are, after completing this section, you should be able to use the concept of resonance to explain structural features of molecules and ions. And then also it says you should understand the relationship between resonance and the relative stability of molecules and ions. So off the bat, the concept of resonance points to the fact that electrons are delocalized. And it points to the fact that Lewis dot structures don't give us the best description, qualitative description as to the arrangement of electrons in a molecule or ion. So that's kind of like an overarching, a general idea or a general answer to that first objective. And then the second objective says understand the relationship between resonance and relative stability. So what is that saying? We understand that delocalization contributes to stability. Delocalization of the electron cloud around the entire molecule contributes to stability, or gives us an idea of stability. It points to the fact that the stabilization or stability of a molecule comes from several things, come from several properties. But one of the things that comes from, or one of the things that contributes to stability of a molecule, is the fact that you have the localization of the electron cloud. And what is that based in? It's based in Coulomb's law, in which you have a positive charge positive charge of the nucleus of the different atoms interacting with the electron cloud. And the more it interacts, the more interactions you have, the lower the potential energy, the more stable the molecule. Systems tend to lower potential energy, and that contributes, and that is another way to say, is tend to more stable configurations, more stable arrangements of the electron cloud. So that's kind of like the overarching solutions, overarching answers to those objectives. But I'm going to show you how I study my material. So let's begin. So let's go through. So the method I want to introduce to you today, if I can just, there we go. The method I want to introduce today is this method that they call survey, question, read, review, and recite. So let's talk about it. So I do this implicitly. The first thing we're going to do is we're going to survey the material. S. We're going to think of the questions in terms of the objectives that we need to achieve when we read this material. So the questions we're going to have in mind are going to be centered around or targeted at the objectives. We're going to read it again. We're going to review it. And then we're going to recite the key ideas that are associated with this piece of work. So SQR, there we go. Survey, question, read, review, recite. So that's how we're going to do this. You can look up other methods if this doesn't work for you, but my goal for you is to understand this material. So let's begin. first thing we're going to do, it says recognizing, drawing, and evaluating the relative stability of resonance. In this case, this is a excerpt from Creative Commons material, the chemistry labor text. So recognizing, let's begin. Recognizing, drawing, and evaluating the relative stability of resonance contributors is essential to understanding organic reaction mechanisms. So that's a big idea. When learning to draw and interpret resonance structures, there are a few basic guidelines to help. It says there's only one real structure for each molecule or ion. This real structure is the resonance hybrid. It takes its character from the average of all the individual resonance contributors, or alternative Lewis dot structures. So when looking at resonance contributors, we are seeing the exact same molecule or ion depicted in different ways. Resonance hybrids are really a single unchanging structure. Okay, and don't confuse resonance structures with tautomerism. Anyway, the resonance hybrid is more stable than any individual resonance structure. So we're just surveying the material. Let's see, the resonance hybrid shows a negative charge being shared equally between two oxygens. 3 resonance contributors do not have to be equivalent. Also, this means the resonance hybrid will be the exact mixture. This means that the resonance hybrid will not be an exact mixture of the two structures. All resonance contributors must be correctly with structures. All resonance contributors must have the same molecular formula, the same number of electrons, and the same net charge. So you also have major and minor resonance contributors. So let's make this more practical. Say I have other things to do. And I need to study this material within 1 or 2 hours. That's the time constraint that I'm given to go through this material. My goal is to get at least a B on this test of this material. So we're making this very practical. I want to get at least a B, so I have other classes I'm studying for. 1. 2, I only have about 2 hours tonight to study, and I'm going to refresh my memory about in like an hour or so tomorrow, within an hour or so tomorrow, and then my test is on the Monday. So for the subsequent days that follow, I'll review this material probably for like an hour or so. So this is my first introduction to this material. So I want to spend about 2 hours. I'm going to condense it for this lecture, of course, but 2 hours I would give a lot to this, my first introduction to this material, 2 hours. So in this 2 hours, the first thing I'm going to do is survey the piece of material. So I'm looking at the material, I'm looking at the main ideas. Typically when people write paragraphs, this goes back to English. Typically when people write paragraphs, the main idea is the first sentence, the topic sentence. So I'm looking at that, keeping that structure in mind as I read. So the main ideas for each paragraph should be in the first sentence or last sentence. The middle portion of the paragraph will give an explanation or exposition as to what is being said for the first or last sentence. So and scientists are very logical in how they write. Typically, they're very logical. They write it with the audience in mind. So we're surveying the material, so we're looking at major and minor resonance contributors, rules for estimating stability of resonance. The resonance structures in which all atoms have complete valence shells is more stable. We're talking about the octet rule. You can annotate and put that on the side. The structures with the least formal charge is more stable. That points to the fact that minimization or minimizing formal charge, having things with not having structures that don't have that many charges. And then 3, the structures with a negative charge and a more electronegative atom will be more stable. So that coincides with chemical logic. The structures with a positive charge and the least electronegative atom is more stable. Very good. That's another idea. The structures with the least separation of formal charge is more stable. Least separation of formal charge is more stable. Good. And then resonance forms are equivalent. That are equivalent have no difference in stability. So we're surveying this material. So this is a little bit beyond general basic chemistry in terms of some of these ideas, but we're only studying that which is relevant to us for general chemistry. So we just surveyed the material, so let's read through it. Recognizing, drawing, and evaluating the relative stability of resonance contributors is essential to understanding organic reaction mechanisms. So as we're reading this, we're going to annotate. So let me get the highlighter. I'm going to highlight first. Some people are proponents of highlighting, some people are not. The reason why I'm highlighting is because when we review, we're highlighting the main ideas, and we're going to annotate based on what we need to associate with that main idea to memorize it. So let's highlight. Okay. So before we get to that, let's make this a little bit. There's only one real structure for each molecular ion. That's something we're going to highlight. Bam. Only one real structure. And what's the structure called? That is the resonance hybrid. So remember, our objective is to understand the concept of resonance, to explain structural features of molecules and ions. That's the first goal we need to achieve. That's the first objective we need to fulfill. So resonance hybrid. Resonance hybrid. So that. Okay. Average of all individual resonance contributors. So look at that. Some people are proponents of rereading. I'm a proponent of rereading. Repetition is good in my opinion. Some people believe you should just read through the material, come up with a set of questions, form a guided inquiry, and then practice going over those questions and over and over and over and over again, and do it with spaced repetition and all those other good stuff. That's good if it works for you. If it doesn't, you have to come up with an alternative method to study, and this is what works for me. And I hope it contributes to your method of studying. You have to be strategic. What are you going to do to learn best? And the material as best as possible, given your time constraints and resource constraints. So let's go through it. There is only one real structure. We have that. One real structure. The structure is the resonance hybrid. And it takes its character from the average of all individual resonance contributors. So you have contributors to the resonance hybrid, and the resonance hybrid is the only real structure. So if I was annotating that, the main thing, if I was annotating that, let's see, text, there we go. So let's annotate this. So if I was writing on this, it would be real structure. Let me just drag this over a bit. Real structure, resonance hybrid. So that would be my first annotation I would put there. I'll put that around the side there, right there. That's like the big idea. And then I would do a next annotation right here. I'm showing you how I study. Okay, so that's the first annotation. And then this hybrid is based on contributors. Those contributors both of the hybrid is based on contributors. Contributors are Lewis dot structures. Actually, let's just say Lewis dot structures. Lewis dot structures. There we go. So that's that. And I'm going to take that and let's just make this a tiny bit smaller. Structures. There we go. That's the first annotation right there. So let's keep reading. So says the resonance hybrid is more stable than any individual resonance structures. So let's see. Resonance hybrid is more stable than any individual resonance structures. So that's another idea. Resonance hybrid is more stable than any individual resonance structures. That's our second main idea. So what am I going to do? I'm highlighting. See, I'm engaging. I'm actively reading the material, not just passively reading it. So let's put in. That's our second idea. And what's that point to? Delocalization. So we want to put it in right there. Why is it more stable? The first thing I associate with that stability, delocalization. And I'm going to, let me see if I can decrease the font size. Actually, let's just put that right here. Delocalization, because that's a big idea. So when I come back to this material on the second or third or fourth day, I have a mind map. I have a place for this material that I've associated with a framework that I already have in my mind from previous ideas, previous discussions, previous concepts. The localization and Coulomb's law. Coulomb's law. And we know, just to further develop that, positive and negative. Lower potential. Okay. So let me see if I can decrease the size of this. Select that, and let's see if we can decrease the size of that. Let's just do that like that. Okay. So the position. Okay. So that's that. So let's keep going. Okay, so we have our second main idea. This is our first reading. First reading. Okay, so let's keep going. Often resonance structures represent a movement of a charge between two or more atoms. The charge is spread out. So that points at the localization idea. Spread out amongst these atoms, and therefore more stabilized when looking at the picture above. Resonance contributors represent the negative charges as being on one oxygen or the other. See, we're further explaining that main idea of it being delocalized, of it being more stable than any individual resonance structure. We're further developing that main idea from the first sentence. When the resonance hybrid, the negative charge is spread out. See, we're still rehashing that same idea of delocalization. Let's go to the third point. Resonance contributors do not have to be equivalent. Okay, so what does that mean? What is that equivalency, or what is that weighting coming from? Okay, it comes from the further ideas we'll discuss in terms of how does it really obey the octet rule? Does each atom have an octet? Does each atom have a complete valence shell? 1. 2. Do we have as less or least as possible? Do we have minimal separation of charge? Have we minimized formal charge? Those types of ideas contribute to the weighting of the resonance structure or resonance contributor to the resonance hybrid. So resonance contributors do not have to be equivalent. Another idea. So what's that pointing to? It points to, let me erase that. It points to This is pointing to the rules that we'll discuss further on. So just keep that main idea in mind. So you have to come up with a framework. You have to come up with a structure that works for you. If you find that your study material is not as engaging, try to find engaging material. There's a lot of free material out there if you have access to the internet. Okay. all resonance contributors must be correct Lewis structures. So that goes back to an idea that we discussed earlier. So actually, let me see. Let me erase that. Highlight on all resonance contributors must be correct Lewis structures. So that's the rules for drawing Lewis structures. And then let's go to the next idea. See, we're trying to maximize time now. Maximize our time, the amount of drawing that we're able to do within a specific time frame. All resonance contributors have the same molecular formula. Yeah, same molecular formula, and same number of electrons, and same net charge. That's that. I'm not dealing with isomers in this class. Not in General Chemistry 1. Okay, that. So the same molecular formula, same number of electrons. Okay, same number of electrons and same net charge. So these are what contribute to how we rate these things. It being a correct Lewis structure, it having the same molecular formula, same number of electrons, same net charge. This is the guidance that we use when we're determining whether this is even a proper contributor, whether it's even a contributor to the resonance hybrid. So let me see. Like that. There we go. The highlighter. And this. That idea, and then that idea. It's that. So that's kind of how I would approach this first page. I hope you see the trend here. We highlight our main ideas, we annotate based on the framework that we have in mind, the previous concepts that we've already gone through, how we can map this on to achieve objectives 1 and achieve objective 2. Hopefully you see what I'm saying, hopefully you understand. If you have any questions, feel free to email me. However, that's what I want you to understand, and we're going to move forward with the lecture today. Okay, let me see. There we go. Let's move forward. Least formal charge, you do the same thing again, just use the associative framework that we have in our mind based off the facts and ideas we've already discussed. So these are more rules for determining resonance, just keep this in your mind. Okay, so let's get to the topic for today, the discussion for today. Okay. Lecture attendance is mandatory, folks. Class assignments are placed on the online platform. We go through this. Office hours occur via Zoom on Mondays and Fridays. Try not to fall behind to make the class for you a more enjoyable experience. Okay, you have an exam coming up on October 26th. So let's talk about Lewis structures and molecular geometry. So we're in chapter 9 in Chemistry Essential Science. I want you to be able to understand and describe three-dimensional shapes of molecules using the valence shell electron pair repulsion theory. It's also called the Gillespie-Nyholm theory. Determine whether a molecule is polar or non-polar based on its geometry and the individual bonding arrangements. Be able to identify the hybridization state. So hybridization is just referring to mathematical mixing of orbitals. That's a short and fast way to describe it. It points to the fact that it points to an idea in the valence bond theory. Be able to sketch how orbitals overlap to form sigma. The sigma comes from the shape and also the fact that on the internuclear axis, sigma and pi perpendicular to the internuclear axis. Perpendicular. Pi bonds, be able to explain the concept of bonding and anti-bonding. So bonding is going to come from the fact that when you have constructive interference occurring with atomic orbitals, that results in a bonding molecular orbital and anti-bonding. When you have destructive interference occurring between molecular orbitals, that results in the anti-bonding molecular orbital, and atomic orbitals equals n molecular orbitals. So the same number, conservation of atomic orbitals. Be able to draw molecular orbital energy level diagrams and place electrons into them to obtain obtain and understand electron configurations of diatomic molecules using molecular theory, and as we'll discuss later on, S&P mixing, that gives you an idea, points to some stability in which the way you arrange that energy level diagram changes as you go between two different atoms or two different diatomic molecules. We'll get into that later. Understand the relationships among bond order, so bond order, bond strength, and bond length. So let's continue. What is bonding? Why is it important? What are the types? And what types of elements tend to participate in the different types of bonding? So bonding is a theoretical construct that involves the attraction of the electrons of an atom to the nucleus of another atom. It's important because it provides a foundation for chemical reactivity. Bonding occurs as a means for elements to share, attract, or distribute electrons in order to become stable. You have three types of bonding that we are going to discuss in this class: covalent bonding, ionic bonding, dative bonding. Covalent bonding occurs when atoms share electrons as a means of bonding. It occurs between nonmetals and nonmetals. Ionic bonding occurs between metals and nonmetals. This is bonding between ions, cations, and non-ions. The bond-orbital cycle gives us a way or a method or a description as to how that structure is formed, how the ionic compound is formed. We discussed that in previous lectures. Dative bonding occurs when one element donates the entire bonding pair of electrons to form a coordinate covalent compound. Typically it occurs between metals and ligands. So let's get to the material we want to discuss for today. So you have three bonding models that we want to just introduce in this class. You have the Lewis model, and helps us understand and make educated predictions about chemical observations. You have valence bond theory. It provides a more quantum mechanical treatment of the electron, but not as delocalized along the entire molecule. And then you have MO theory, which is like the creme de la creme for this class. It provides a full quantum mechanical treatment of the molecule and its electrons as a whole. Lewis model is named after Gilbert and Lewis, and you have the valence electrons represented as dots. Your electrons are forming your bonds represented as sticks. And you have chemical symbols to depict the molecules. So let's just go through this again. One thing, so note, place, subtract, intro, minimize. So NP-SEM, NP-SEM, SEM. So note the total amount of valence electrons. Place single bonds between each atom. So let me make sure you understand what I'm saying. Let me make sure. P SEM. NP-SEM. So note, place, subtract, intro, minimize. Note the total amount of valence electrons. P, place single bonds between each atom. S, subtract 2 electrons based on the number of bonds added. E, ensure each atom has an octet. Exceptions are with atoms with expanded octets occurring in the third period, and also exceptions occur with your incomplete octets, for example with boron and beryllium. Then you minimize charges. These are the ways you draw really good Lewis dot structures, really good contributors to the resonance hybrid. So let's keep going. Let's keep going. Okay, so bonding theories help us predict the circumstances under which bonds form and also the properties of resultant molecules. Chemical bonds form because they lower the potential energy between the charged particles that compose the atoms. Metals and nonmetals result in ionic bonds. Non-metals and nonmetals typically result in covalent bonds. And metals and metals typically result in metallic bonding. So we've already discussed how to do electron configurations. We've already discussed the bond-orbital cycle. So let's get to what we want to discuss for today. So in terms of common polyatomic ions, I will want you to understand the really, really common ones. And I'm going to, for this class, so for example, I want you to know your perchlorate. I want you to know permanganate. There's a minus charge. I want you to know sulfite. Let me do this a little bit better. Okay, so I want you to know. Here we go. I want you to know chlorate. I want you to know perchlorate. I want you to know permanganate. I want you to know sulfite. I want you to know sulfate. I want you to know cyanide. I want you to know ammonium. I want you to know phosphate. I want you to know nitrate, hydroxide. That's the thing we talk about a good bit. Carbonate, bicarb. And that's as much as I want you to know. So here, erase. Here we go. There we go. Let's keep going. Okay, let's go. We already discussed resonance. So let's talk about VESPA. So VESPA, valence shell electron pair repulsion theory. Big ideas. You minimize repulsions between electron groups and you maximize distances, and you want to maximize the bonding interaction. So let's keep those big ideas in mind. Minimize repulsions between electron groups, maximize bonding interactions, maximize distance between those things, and you want to keep those things in mind. So linear beryllium chloride. So say for example we have this is a classic example of a linear molecule. I'm using a model kit. If you don't, or if you can't afford a modeling kit, you can use gumdrops, you can use styrofoam, you can use anything or it's gumdrops and toothpicks. You can do a lot of things with gumdrops and toothpicks. And you can use toothpicks as the bonds and gumdrops as the different atoms. But I'm using a modeling kit for this video, this lecture video this afternoon. So this is beryllium chloride. This is a linear molecule. We can also use this a shape to describe carbon dioxide. However, in carbon dioxide you have double bonds. Okay, so trigonal planar. Boron trifluoride. Trigonal planar. Trigonal in one plane. Trigonal planar. Or a better way to draw that. A better way to do that. Trigonal planar. There we go. Trigonal planar. Trigonal. One plane. Trigonal planar. Okay, so let's talk about methane. Methane, tetrahedral. See? Tetrahedral. There are 4 faces. Tetrahedral. Okay. PCl5, trigonal bipyramidal. Trigonal bipyramidal. You have your trigonal face right there, and it's bipyramidal. Okay. Then you have your octahedral shape. There you go. So octahedral. Yes, this is going to work. There you go. Octahedral. I just want you to see the shape of them. Octahedral. See, we have 6 electron groups. 1, 2, 3, 4, 5, 6. Someone pointed out in class that the vertices. So an analogous way to think about this, the vertices in the shape in some way do correspond to the electron groups. So if you keep in mind that if I'm talking about electron groups, and also one thing to always specify when you're talking about molecular shape, do you want the molecular geometry or do you want the electron geometry? Because they can be different at times. Because I can have 3 electron groups, but one of those groups can be a lone pair. And if that's a lone pair, it may not be. So I may have 3 electron groups. If one's a lone pair, instead of it being linear, it will be bent. And we'll get to that later on. So octahedral, for example, sulfur hexafluoride. So all molecules have particular shape. The shapes are determined by looking at the arrangement of electron bonding and non-bonding pairs. correct Lewis dot structures provide the ability to predict common molecular shapes. We are able to determine molecular shape by looking at the angles and distances between the nuclei and the electrons. Remember, single bonds are sigma bonds, double bonds are sigma and pi, triple bonds and sigma are sigma and 2 pi. So that's kind of pointing to MO theory concepts, MO theory ideas, but I just want to expose you to it now. So this is a link you can use to look at simulations from Oxford University. So questions to consider when assigning molecular shape. Let's just go through these questions. So for those who do inquiry as they read, do we have the correct Lewis dot structure? How many bonds do we have? What type of bonds are they? And remember, single bond, double bond, triple bond, lone pair, all of those fall under the umbrella. They fall under the umbrella of an electron group. Single bond, double bond, triple bond, lone pair, or non-bonding pair. In this context, those terms can be interchangeable. Non-bonding pair, lone pair, fall under the umbrella of electron group. So how many electron pairs are non-bonding pairs? Where are the non-bonding pairs? Let me show you. We keep on talking about these non-bonding pairs. Let me show you. So say for example, we had some molecule. Say we had water. This is water has 2 lone pairs. Okay, water has 2 lone pairs. So say I said I want the molecular geometry of water. Let me show you a classic example of this. So I said I want the molecular geometry of water. So look right here. Let me narrow this into you. So this is an example of me building it. It's going to be V-shaped or bent. However, so this is the molecular geometry, the geometric shape. However, the number of electron groups that we have is 4. You have 4 electron groups in this thing. So it's important for you to specify, do you want the electron geometry? Do you want the molecular geometry? Typically, people want the molecular geometry, they want the molecular shape. So this is what we're referring to here. It's bent, but it has 4 electron groups. So just keep that in mind. Let that question loom in your mind. So more questions to consider. Where are the non-bonding pairs? Because if they're not on the central atom or the atom that really determines the shape of the molecule, it's not going to be heavily considered, at least for the particular question you're looking at. Are there deviations from this ideal description? So valence-shell electron pair repulsion theory allows us to understand molecular geometry. In VSEPR, that's a short way to say it, VSEPR, we arrange electron pairs to minimize electron pair repulsion and maximize distance and bonding interactions. So this is what I'm showing you here. So say we have 4 electron groups with 2 are lone pairs, 2 are atoms, 2 are single bonds, 2 are lone pairs, 2 are single bonds. This is an example of water. Or sulfur dichloride. Against that. So let's look at another one. Say for example, we had, so this is an example of an octahedral one in which we have 6 electron groups and 6 are single bonds. However, say we had 2 of those electron groups as lone pairs. 1, 2. So we have something that's square planar. So let me just show you. The power of being able to build it yourself. Learn by doing. This is for those who are proponents of that. Learn by doing. So see, square planar, it's in one plane. See, it's in one plane, square planar. However, it has 6 electron groups. The power of building it yourself. When you build it yourself, it makes a little bit more sense. You're able to flesh out the concepts more. So that's what we're pointing to in this lecture today. So we can have 6 electron groups and they can be T-shaped. That means you have 3 lone pairs. 3 non-bonding pairs. I'm going to use the same color for these so we know what we're referring to in this. Because you can have different colors for your lone pairs. Not in actuality, I'm talking about for the modeling kit. So say we have three non-bonding pairs, and it's T-shaped, but we have 6 electron groups. So another way for us to phrase this: find the number of electrons the central atom normally has in its valence shell. Add 1 electron to every atom that the central atom is bonding to. This is just one way to go through it. Or you can remember, the main idea I want you to take away from this is arrange electron pairs in the correct shape. Okay, so in terms of repulsions, lone pair, repulsion for this discussion is greater than bonded pair to lone pair, which is greater than bonded pair to bonded pair. The main idea I want you to take away from this discussion is use the proper rules, use the correct rules to draw your Lewis dot structures. And when you do that properly, when you write good Lewis dot structures, it can help you make or write and understand good resonance contributors. And from those good resonance contributors, you can determine the resonance hybrid. That's one thing you can do with a good set of Lewis dot structures. 2, when you draw the correct Lewis dot structures, you can apply that Lewis dot structure, use that Lewis dot structure to understand the molecular shape, or predict to a certain extent the molecular shape. It may not correspond exactly with what we see, and that's the reason why we have to use valence bond theory. For example, with hydrogen sulfide, you have deviations from it. Instead of it being completely linear, you have deviations. So hydrogen sulfide, or instead of it being tetrahedral, whatever the case may be, you have deviations. Whatever geometry you're referring to in this case, molecular shape or electron geometry or molecular geometry, you have deviations. But when you draw correct Lewis dot structures, you are able to understand molecular shape, you are able to determine good resonance contributors and look to see or approximate to what the resonance hybrid would be. It's a very useful tool. And also in organic chemistry, we know that when we draw good Lewis dot structures, we can kind of give a description as to what's occurring, the mechanism as to how the reaction is occurring. So Lewis dot structures are very useful. Okay. So VSEPR is based on the simple idea that electron groups, which we define as lone pairs, single bonds, multiple bonds, and even single electrons, repel one another through Coulombic forces. So you want to make sure you're looking at the central atom. So valence bond theory. So say for example, remember we talked about this conceptual baton passing, in which we had Max Planck passing it on to Albert Einstein. Actually, excuse me, we had Niels Bohr. We had Max Planck passing it on to Albert Einstein, and then you had Einstein passing it on to Niels Bohr, and then we had Niels Bohr passing it on to Werner Heisenberg. So what I'm saying is typically a way for you to process the concepts. So same way we did that for this thing, we can go from Lewis dot Lewis dot structures. Say if Lewis dot structure was the concept, the main idea, the person with the baton, passing it on to valence bond theory, and then valence bond theory passing it on to molecular orbital theory. This is a way to process the concepts so that you can build on it if this works for you. Okay, valence bond theory is a more advanced theory on which is an application of a general quantum mechanical approximation method called perturbation theory. We're not going deep into that. This is not quantum mechanics class, just want to expose you to it. So in many cases, these orbitals are just sp, d, and f. In other situations, the orbitals are hybridized. VBT, valence bond theory, we calculate the effect of these interactions on the energies in the atomic orbitals. So when we apply valence bond theory to a number of atoms and their corresponding molecules, we arrive at the following general observation. The interaction energy is usually stabilizing or negative when the interacting atomic orbitals contain a total of 2 electrons that can spin pair with opposing spins. So a chemical bond is a result of the overlap of 2 half-filled orbitals with spin pairing of the 2 valence electrons. And then also the geometry of the overlapping orbitals determine the shape of the molecule. So VSEPR predicts that dihydrogen sulfide, this is what I was pointing to earlier, has a bond angle of 109.5. but VBT, excuse that, it should be 92 degrees, not 92 degrees Celsius. Predictions coincide better with experimental results of a bond angle of 92. Okay, so that comes from the fact that Vesper gives us an idea, VBT gives us a better idea. A further or more complete explanation, that's a better way to put it. So VBT accounts for the bonding in methane and other polyatomic molecules by incorporating an additional concept called orbital hybridization. So hybridization, the mathematical mixing of atomic orbitals to form hybrid orbitals. This is where you get these ideas of SPDF or SP2, SP, SP3D, SP3D2. That's referring to the mixing. So it's a mathematical procedure in which standard atomic orbitals are combined to form new hybrid orbitals that correspond more closely to the actual distribution of electrons in the chemically bonded atoms. A chemical bond is the overlap of two orbitals that contain two electrons. The greater the overlap, the stronger the bond and the lower the energy. In hybrid orbitals, the electron probability density is more concentrated in a single directional lobe, allowing greater overlap with orbitals of other atoms. So we're going to just keep on going. Hybrid orbitals minimize the energy of the molecule by maximizing the overlap in a bond. So this is like hinting to or based in the Coulomb's law, ideas from Coulomb's law. So let's talk about MO theory. So this is just an overview, this is just introduction. So this lecture is like introduction to these ideas, and you have to go and do your readings, go and practice the homework. So you play a part, I play a part in this learning process. I help to facilitate, we break up the ground, we help with conceptual ideas forming, helping you see where you can put in your associative framework for learning and andragogical ideas, and then you are able to apply the concepts. You are able to associate it with something you know, and you're able to learn it and flesh this out and make this more real to you. Develop your scientific intuition, all those things. Use these as ideas you can apply in your classroom, apply in other research settings, all of that. So MO theory, this is just an orbital diagram. We have a sigma, sigma star, sigma referring to our bonding orbital, sigma referring to our bonding orbital, sigma star referring to our antibonding, sigma, and you have a pi star, sigma star. In MOT, we do not actually solve Schrodinger's equation or molecule directly. Instead, we use a trial function, an educated guess. The trial function we use in this case would be LCAOs, a linear combination of atomic orbitals. However, no matter how good our guess, nature is the best at minimizing the energy of the orbital. The simplest trial function that we are going to use in this class is LCAOs, linear combinations of atomic orbitals, which is basically a weighted linear sum of the valence atomic orbitals of the atoms in the molecules. So this big idea that I pointed to earlier, n atomic orbitals equals n molecular orbitals. Sigma orbital, the name is derived from the shape and position on the internuclear axis, and pi orbitals, the shape and position, name is derived from the shape and the position perpendicular to the internuclear axis. So antibonding orbital, you have destructive interference results in MO higher than the energy for the atomic orbitals. This MO is an antibonding orbital. Bonding orbitals are derived from the constructive interference that occurs with that results in a MO lower in energy than the atomic orbital. This is your bonding. And then the bonding MO. So bond order is 0.5 in brackets. You look at the electrons in your bonding molecular orbitals minus the electrons in antibonding molecular orbitals, and you multiply that whole difference by 0.5. So this is what I was pointing to earlier. I want you to take note of this. Take note of this. You see, as you go from diatomic nitrogen to diatomic oxygen, you have a switching. You have a switching of the order. So you go from pi 2p to sigma 2p, and then for oxygen, diatomic oxygen, you go from sigma 2p to pi 2p. So where does that come from? We're not going into a deep quantum mechanical explanation for that. This is a general chemistry class. What we're going to do is get the main idea, get the short summary, condensed answer for that question. Why does the order change? The bottom line is that S&P mixing is significant in diatomic boron, carbon, and nitrogen, but not in diatomic oxygen, fluorine, and neon. That's the surface level. That's just what we're going to talk about for that. So MO theory, let's continue. MO theory helps us understand diamagnetism, in which you have paired electrons, or paramagnetism, in which you have unpaired electrons. And you can see an example of this with supercooled oxygen being held up between two magnets. So our references, those are our references, and that's where we're going to end off our discussion today. Once again, it was so good to have you in lecture today. So good to see you. So good to know that you're in my class. Excited to have you in my class. I want everyone to know that you're not alone. Keep up the work that you're doing. Keep pushing. Keep going. We're cheering you on.
In the heart of the cell where secrets dwell, lies the nucleus, a masterful genesis. Chromatin networks dancing in twists and swirls, holding the codes, the stories untold. O nucleus in your chromosomal embrace, regulating life with elegance and grace. Gene expression, in your controlled procession, you weave the fabric of our very essence. With histones and nucleosomes, a tightly wound script, epigenetic mysteries in a chromatic crypt. Transcription factors binding, with a rhythmic swing, promoters and enhancers make the cellular world sing. O nucleus, a dynamic domain so crucial, in cancer's shadow your balance becomes crucial. Gene silencing and activation in a delicate dance, in the story of life you lead the advance. Splicing and dicing RNA in formation, mRNA travels with vital information. From the depths of the nucleus to the cytoplasmic seas, a journey of codes unlocking life's mysteries. In the nucleus where genetic fates intertwine, mutations whisper, the onset of a malignant sign. Oncogenes and suppressors in a delicate play, when the balance tips the cellular order sways. O nucleus, in your realm so profound, life and death in your cycles are bound. In the dance of genes, under the bossa nova sky, you hold the key where the answers lie. In the swing of life, in the rhythm of existence, the nucleus endures with resilient persistence. In the bossa nova beat, hear the cellular song, in the heart of the cell where the truths belong.
Purpose of these episode, these are not at all for medical advice or suggestions, we disclaim any loss in any way. These episodes are for educational purposes only, and are not for medical advice or suggestions. The views of this podcast represent those of my guest, S, and I. Adsorption principles in pharmaceuticals. 1. Thermodynamics, study of energy and its transformations in diffusion. 2. Kinetics, study of the rate of diffusion processes. 3. Passive transport, movement of molecules without energy input. 4. Facilitated transport, movement of molecules with the aid of a carrier. 5. Active transport, movement of molecules against a concentration gradient. 6. Fick's law of diffusion, mathematical model describing the rate of diffusion. 7. Lag time effect, delay in drug diffusion from a delivery device. 8. Burst effect, sudden release of a large amount of drug from a device. 9. Brownian motion, random movement of particles in a fluid. 10. Equilibrium, state where no concentration gradient exists. 11. Osmosis, movement of solvent, usually water, across a membrane. 12. Pinocytosis, cellular process of engulfing fluids. 13. Endocytosis, cellular process of engulfing solids. 14. Phagocytosis, cellular process of engulfing large particles. 15. Diffusion coefficient, measure of molecule permeability in cm2/S16. Fick's first law, J equals ddc/dx, shows flux proportional to concentration gradient 17. Fick's second law, dm/dt equals ds, dc/dx, relates concentration gradient to transport rate 18. Partition coefficient, relates drug concentrations in membrane to compartments 19. Sink conditions, state where CR is nearly zero, no drug accumulation 20. Permeability coefficient, P equals dk/H, measures membrane permeability in cm/S21. Zero order process, constant rate transport, slope equals PSCD22. Transdermal patch, delivery system for zero order drug transport 23. Inverted closed loop intestinal model, used to study oral drug absorption 24. Lag time, delay before drug release in controlled systems 25. Burst effects, non-constant drug release from controlled systems 26. Lag time effect, time for drug to saturate tissue before absorption 27. Burst effect, rapid release from presaturated membranes 28. Diffusion, main force for drug release in sustained release products 29. Reservoir systems, devices with drug core surrounded by rate controlling membrane 30. Matrix systems, drug dispersed evenly in a matrix for slow release 31. Fick's law, governs release from reservoir systems, enabling zero order release 32. Dose dumping, instantaneous release of excess drug from reservoir system 33. Ethyl cellulose, commonly used for rate limiting membrane in oral formulations 34. Diffusional reservoir systems, should not be cut, broken, or chewed to avoid toxicity adsorption principles in pharmaceuticals 35. Drug diffusion, occurs through rate controlling membrane for systemic delivery 36. Drug absorption, occurs by diffusion in gastrointestinal tract and other sites 37. Dissolution step, rate limiting step for drug absorption of low aqueous soluble ITY drugs 38. Partition coefficient, factor governing drug absorption in gastrointestinal tract 39. Controlled and sustained release formulations, designed to release drugs slowly for absorption control 40. Molecular weight, affects drug absorption, high weight compounds may not be absorbed 41. Paracellular transport, drug movement between cells by convection 42. Transcellular route, drug transport through cells by diffusion 43. pH partition hypothesis, suggests drugs penetrate membranes in unionized form based on pH 44. Henderson-Hasselbalch equation, relates pH, pKa, and drug ionization for absorption prediction 45. Chemical equilibrium, dynamic balance in reactions with constant recetant/product concentrations 46. Bronsted-Lowry theory, defines acids as proton donors and bases as proton acceptors 47. Ionization of weak electrolyte, Bronsted-Lowry representation of weak acid ionization in water 48. Law of mass action, states rate of forward reaction is proportional to reactant concentration 49. Specific reaction rates, proportionality constants in forward and reverse recessions 50. Dissociation constant, constant for weak acid ionization, denoted as Ca 51. Dissociation constant, constant for weak acid ionization, denoted as Ca 52. Ca, ionization constant for weak acids, equals H3O plus A/Ha 53. General form of equation, representation of weak acid ionization, Ha plus H2O. H3O plus A54. Kb, ionization constant for weak bases, equals OBH plus /B55. Kw, dissociation constant of water, equals 1x1014 at 250 C56. pH scale, Sorensen's scale, defined as log H3O plus 57. Isotonic solution, solution with equal osmotic pressure to another solution 58. Tonicity, effect of a solution on cell shape due to osmotic pressure 59. Crenation, red blood cell shrinkage in a hypertonic solution 60. Hemolysis, red blood cell bursting in a hypotonic solution 61. Isotonicity importance, critical for injectables, ophthalmic, nasal, and irrigation solutions adsorption principles in pharmaceuticals 62. Freezing point depression method, technique to calculate solution tonicity 63. NaCl equivalent method, Method to adjust tonicity in pharmaceutical system 64. Isotonic solution, solution with equal osmotic pressure to body fluid 65. Freezing point depression method, calculates isotonicity by freezing point change 66. Sodium chloride equivalent method, determines isotonicity based on NaCl equivalent weight 67. TF, change in freezing point caused by a solution 68. E-value, weight of NaCl per 1 gram of substance 69. Adsorption, accumulation of molecules at an interface 70. Absorption, penetration of absorbing material by absorbed substances 71. Free energy, state of energy in a system available to do work 72. Adsorption of gases, displacement of air by another gas 73. Adsorption from solution, displacement of solvent molecules by a more strongly adsorbed solute 74. Solid-gas interface, boundary between a solid surface and gas phase 75. Physical adsorption, weak attractions like gas condensation 76. Chemisorption, chemical reaction at the surface 77. Reversibility, ability to remove adsorbate easily 78. Effect of temperature, temperature impact on adsorption amount 79. Monolayer, single layer adsorption at low pressure 80. Adsorption isotherms, relationship between adsorption amount, adsorbent mass, and gas pressure 81. Freundlich equation, relates adsorption amount to equilibrium pressure 82. Type I adsorption isotherm, monolayer adsorption followed by saturation 83. Type II adsorption isotherm, sigmoidal shape indicating multi-layer formation 84. Adsorption from solution, solute adhesion from a liquid solution 85. Selective adsorption, preferential adsorption of specific solutes 86. Van der Waals forces, weak intermolecular forces in physical adsorption. Adsorption principles and applications 1. Desorption, reverse of adsorption, based on similar principles 2. Ionic solutes, substances that may be desorbed by pH changes 3. Saponin, strongly adsorbed substance used to displace materials 4. Decolorization, process using charcoal to obtain colorless solutions 5. Water vapor adsorption, alumina and silica gel adsorb up to 40% water 6. Kaolin, adsorbs intestinal toxins by ion exchange 7. Activated charcoal, emergency antidote for alkaloid poisoning 8. Adsorption chromatography, separation technique based on adsorbent affinity 9. Surface area determination, method to measure specific surface area 10. Nonspecific adsorption, adsorption of drugs, nutrients, and enzymes 11. Contact angle, angle indicating wetting problems, 90 degrees, 12. Wettability, ability to wet, improved by surfactants 13. Suspension preparation, process to obtain uniform drug particles 14. Emulsion preparation, process involving surface and interfacial principles 15. Neosomal formulations, novel drug delivery systems in trial 16. Antacids, partially adsorbed stomach gas, containing simethicone to reduce bloating 17. Taste masking drugs, drugs like diazepam adsorbed onto substrates to improve taste 18. Adsorption of water vapor, alumina and silica gel adsorb water vapor effectively 19. Surface area determination, method to determine specific surface area per unit weight/volume 20. Effect on drug absorption, certain substances reduce absorption of medicaments from the alimentary tract 21. Drug interactions via adsorption, nonspecific adsorption of drugs, nutrients, and enzymes 22. Adsorption to plastics, drugs like insulin and diazepam adsorb significantly to forgiving sets 23. Micromeritics, science studying small particles characteristics like size, shape, and density 24. Particle size distribution, key component in drug design and delivery 25. Porosity, property studied in micromeritics related to particles void spaces 26. Flow properties, characteristics of particles related to their movement 27. Angle of repose, property studied in micromeritics related to particles stability 28. Bulkiness, property related to the overall volume of particles 29. Particle size, size of drug particles affecting absorption and duration 30. Monodisperse, pharmaceutical powders with uniform particle size adsorption principles and applications 31. Particle size distribution, range of particle sizes in a sample, often expressed in diameter 32. Surface area, area of particles exposed for interaction 33. Particle size terminology, units, mm, m, nm, pm, fm for different scales 34. Optical microscope, measures particle size by projected diameter 35. Sieving method, common analysis method using stacked sieves 36. Sedimentation, method for determining particle size in colloidal systems 37. Stokes diameter, particle size expressed in subsieve range using Stokes law 38. Bulk volume, total volume of solid particles and void spaces in a powder 39. Void volume, volume of spaces between solid particles in a powder 40. Andreasen apparatus, device for particle size estimation using gravity/sedimentation 41. Voids, empty spaces in powder 42. Particle density, mass per unit volume of particles 43. Bulk density, powder mass per bulk volume 44. Granule density, density of powder granules 45. True density, density of solid powder particles 46. Interparticle porosity, void between particles 47. Intraparticle porosity, void within granules 48. Flow properties, characteristics affecting powder flow 49. Free-flowing, smooth particles with low porosity 50. Cohesive, particles with cohesive forces 51. Angle of repose, maximum angle of powder pile 52. Carr's compressibility index, measure of powder compressibility 53. Hausner ratio, ratio indicating powder flow 54. Hausner ratio, ratio of tap density to port density indicating flow 55. Coulter counter method, measures particle volume for size distribution analysis 56. Specific surface, surface area per unit weight or volume of material 57. Adsorption method, measures gas adsorption to determine surface area 58. Air permeability method, measures resistance to fluid flow through powder 59. Avogadro number, used to calculate surface area from adsorbent quantity 60. Fisher-Ziev sizer, instrument measuring particle size via airflow 61. Poiseuille's equation, formula relating fluid flow through capillaries to pressure 62. Kozeny-Kármán equation, derived from Poiseuille's equation to estimate surface area 63. Laminar flow, smooth, orderly flow with minimal disruption 64. Kozenius constant, constant in the Kozeny-Kármán equation for flow estimation adsorption principles and applications 65. Capillaries, tiny passages where fluid flows through powder bed 66. Batch-to-batch variations, differences in powder characteristics between production runs. Some content was made using AI in the realm of pharmaceuticals, where compounds are keen. Here's a mnemonic verse, to remember what each term means. Thermodynamics, the very first step, energy in motion, its secrets adept. Kinetics follows, with rates so profound, the speed of diffusion, where answers are found. Passive and facilitated, transport types 2, moving molecules, with or without a Q. Actives the third, against the gradient it fights, transporting molecules to unprecedented heights. Fick's laws, first and second, guiding diffusion's rate, mathematical models that scientists appreciate. Lag and burst effects, in delivery they play a part, controlling drug release, they're an essential art. Brownian motion, particles in a dance, random movements in fluid, given a chance. Equilibrium's balance, no gradient in sight, where concentrations level, everything's just right. Osmosis, pinocytosis, processes so neat, moving water and engulfing, they never admit defeat. Endocytosis and phagocytosis, cellular intake, engulfing solids and large particles, for the cell's own sake. Diffusion coefficient, a measure to know how permeable a molecule, how easily it will flow. Partition and permeability, coefficients of their own, describing how drugs through membranes are shown. Zero-order processes, constant and sure, a steady rate of transport, continuously pure. Transdermal patches, inverted models, quite the sight, for studying absorption, they bring much insight. Reservoirs and matrix systems, controlled release they ensure, with fixed law governing, their effect is pure. Ethyl cellulose membranes, diffusional systems to heed, cutting them is risky, toxicity could proceed. Drug diffusion and absorption, key processes in play, with dissolution steps, leading the way. Controlled and sustained formulations, designed with care, for slow drug release, absorption control to spare. Molecular weight, paracellular paths, influence absorption, guiding pharmacokinetics graphs. Transcellular routes, and the pH partition hypothesis, predicting drug penetration, a scientific synthesis. Chemical equilibrium, Brønsted-Lowry's guide, with ionization, and the law of mass action by its side. Specific rates, dissociation constants, to understand, the ionization of weak acids, in water's hand. Ka and Kb, constants of ionization, defining acids, and bases, in aqueous solution. The pH scale and isotonicity, parameters to measure, for solutions' effects on cells, and their pressure. Freezing point depression, NaCl's equivalent role, in adjusting tonicity, they take control. Adsorption and absorption, processes defined, with free energy and adsorption of gases, intertwined. Physical and chemisorption, adsorption's two faces, with reversibility and temperatures traces monolayers and isotherms, adsorption to discern, Freundlich's equation, and isotherm types to learn. Desorption, ionic solutes, and saponins might, in displacing materials, they show their fight. Decolorization and water vapor adsorption's role, in creating clearer solutions, they take their toll. Kaolin and activated charcoal, adsorbents so grand, in emergencies and toxin removal, they lend a hand. Adsorption chromatography, a separation technique, with surface area determination, the specifics we seek. Nonspecific adsorption, contact angles clue, in preparations of suspensions and emulsions, 2. Neosomal formulations, antacids relief, taste masking and adsorption of water, beyond belief. Micromeritics, the study of small, particle size and porosity, they cover it all. Flow properties, angle of repose, in powders and granules, how stability shows. Bulkiness and particle size, characteristics defined, in drug design and delivery, they're intertwined. Monodisperse powders, uniformity's key, for consistency in therapy, as clear as can be. In pharmaceuticals, where precision's the norm, this mnemonic poem helps knowledge transform. The journey through principles of adsorption setting the stage, Thomas Jefferson Memorial, D.C. On a bright spring morning, Professor Avery gathers her students at the Thomas Jefferson Memorial. The group stands in awe of the towering figure of Jefferson, surrounded by his words on innovation and progress. Professor Avery begins, "Today, we embark on a journey through the principles of adsorption, guided by the landmarks around us, starting here, where innovation meets history." Chapter 1, Thermodynamics and Kinetics at Shenandoah National Park, VA. The group travels to the lush landscapes of Shenandoah National Park amidst the backdrop of cascading waterfalls and verdant valleys. Professor Avery introduces two characters, Theo the thermodynamicist and Kim the kineticist, both exploring the park's natural energy flows. Theo marvels at the sun's energy transforming the landscape, while Kim races against time, measuring the speed of streams. The students, divided into teams, engage in a scavenger hunt, each clue relating to energy transformations or the rates of natural processes, embodying the essence of thermodynamics and kinetics. Chapter 2, Transport Mechanisms at the Smithsonian National Air and Space Museum, DC. Next, the class finds themselves under the vast canopy of the Smithsonian National Air and Space Museum. Here, they meet Pat the passive, who glides effortlessly through the air exhibits, Faiza the facilitator, who aids in navigating the museum's sections, and Adam the active, who challenges himself against a flight simulator's forces. The students, inspired by these characters, debate which exhibit best represents each transport mechanism, drawing parallels to molecular movement in pharmaceuticals. Chapter 3, Fick's Laws and Effects at Great Falls Park, VA. At Great Falls Park, the roaring waters serve as the perfect backdrop for understanding Fick's laws. Fiona and Lawrence, two fictional characters embodying Fick's first and second laws, guide the students in predicting where the water will flow fastest and why. Through experiments with water flow and pebble barriers, the group visualizes diffusion rates and concentration gradients in a tangible, memorable manner. Chapter 4, Transport Phenomena at United States Botanic Garden, DC. In the serene environment of the United States Botanic Garden, the students meet Brooke the Brownian, oscillating randomly among the plants, embodying the random movement of particles. Ozzy the osmotic demonstrates water transport through semi-permeable membranes of the garden's water features. This picturesque setting helps students grasp the complexity of molecular movements and equilibrium in nature and pharmaceuticals. Chapter 5, Cellular Processes at Mount Vernon, VA. Mount Vernon, with its expansive estates and selective entry points, becomes the stage for understanding cellular processes. Characters like Penny the pinocytotic and Eddie the endocytotic engage the students in a role play, demonstrating how the estate's management mirrors cellular uptake mechanisms, making the abstract concepts of cellular transport relatable and understandable. Chapter 6, Diffusion in Drug Delivery at Virginia Beach. The journey continues at Virginia Beach, where the rhythmic tides illustrate the principles of drug diffusion. Dr. Dara Diffusion and Perry Partition, two researchers, discuss their latest findings by the shoreline, comparing the ebb and flow of the tides to the mechanisms of drug release in transdermal patches. The students, inspired, construct sand models to represent different drug delivery systems, exploring the impact of environmental conditions on diffusion rates. Epilogue, interactive quiz and summary at Lincoln Memorial, DC. The final chapter unfolds at the Lincoln Memorial, where the students, now imbued with knowledge and memories, participate in a grand quiz. Each question transports them back to a landmark, recalling the adventures of Theo, Kim, Pat, and the others. Professor Avery concludes, just as these monuments stand testament to our history and achievements, so too do the principles of adsorption underpin advancements in pharmaceuticals. As the sun sets over the reflecting pool, the students reflect on their journey, not just through the landmarks of Virginia and DC but through the landscapes of scientific discovery. This experiential lesson, woven with stories and characters, ensures that the principles of adsorption are not merely learned but lived and remembered. Adsorption principles in pharmaceuticals. 1. Thermodynamics, study of energy and its transformations in diffusion. 2. Kinetics, study of the rate of diffusion processes. 3. Passive transport, movement of molecules without energy input. 4. Facilitated transport, movement of molecules with the aid of a carrier. 5. Active transport, movement of molecules against a concentration gradient. 6. Fick's law of diffusion, mathematical model describing the rate of diffusion. 7. Lag time effect, delay in drug diffusion from a delivery device. 8. Burst effect, sudden release of a large amount of drug from a device. 9. Brownian motion, random movement of particles in a fluid. 10. Equilibrium, state where no concentration gradient exists. 11. Osmosis, movement of solvent, usually water, across a membrane. 12. Pinocytosis, cellular process of engulfing fluids. 13. Endocytosis, cellular process of engulfing solids. 14. Phagocytosis, cellular process of engulfing large particles. 15. Diffusion coefficient, measure of molecule permeability in cm2/S16. Fick's first law, J equals ddc/dx, shows flux proportional to concentration gradient 17. Fick's second law, dm/dt equals ds, dc/dx, relates concentration gradient to transport rate 18. Partition coefficient, relates drug concentrations in membrane to compartments 19. Sink conditions, state where CR is nearly zero, no drug accumulation 20. Permeability coefficient, P equals dk/h, measures membrane permeability in cm/S21. Zero order process, constant rate transport, slope equals PSCD22. Transdermal patch, delivery system for zero order drug transport 23. Inverted closed loop intestinal model, used to study oral drug absorption 24. Lag time, delay before drug release in controlled systems 25. Burst effects, non-constant drug release from controlled systems 26. Lag time effect, time for drug to saturate tissue before absorption 27. Burst effect, rapid release from presaturated membranes 28. Diffusion, main force for drug release in sustained release products 29. Reservoir systems, devices with drug core surrounded by rate controlling membrane 30. Matrix systems, drug dispersed evenly in a matrix for slow release 31. Fick's law, governs release from reservoir systems, enabling zero order release 32. Dose dumping, instantaneous release of excess drug from reservoir system 33. Ethyl cellulose, commonly used for rate limiting membrane in oral formulations 34. Diffusional reservoir systems, should not be cut, broken, or chewed to avoid toxicity. 1/3 Adsorption principles in pharmaceuticals. Study online at https://quizit.com/_EO51M35. Drug diffusion, occurs through rate controlling membrane for systemic delivery 36. Drug absorption, occurs by diffusion in gastrointestinal tract and other sites 37. Dissolution step, rate limiting step for drug absorption of low aqueous solubility drugs 38. Partition coefficient, factor governing drug absorption in gastrointestinal tract 39. Controlled and sustained release formulations, designed to release drugs slowly for absorption control 40. Molecular weight, affects drug absorption, high weight compounds may not be absorbed 41. Paracellular transport, drug movement between cells by convection 42. Transcellular route, drug transport through cells by diffusion 43. pH partition hypothesis, suggests drugs penetrate membranes in unionized form based on pH 44. Henderson-Hasselbalch equation, relates pH, pKa, and drug ionization for absorption prediction 45. Chemical equilibrium, dynamic balance in reactions with constant reactant/product concentrations 46. Brønsted-Lowry theory, defines acids as proton donors and bases as proton acceptors 47. Ionization of weak electrolyte, Brønsted-Lowry representation of weak acid ionization in water 48. Law of mass action, states rate of forward reaction is proportional to reactant concentration 49. Specific reaction rates, proportionality constants in forward and reverse reactions 50. Dissociation constant, constant for weak acid ionization, denoted as Ca 51. Dissociation constant, constant for weak acid ionization, denoted as Ca 52. Ca, ionization constant for weak acids, equals H3O plus A/Ha 53. General form of equation, representation of weak acid ionization, Ha plus H2O. H3O++ A54. Kb, ionization constant for weak bases, equals OBH /B55. Kw, dissociation constant of water, equals 1x1014 at 250 C56. pH scale, Sorensen's scale, defined as log H3O+ 57. Isotonic solution, solution with equal osmotic pressure to another solution 58. Tonicity, effect of a solution on cell shape due to osmotic pressure 59. Crenation, red blood cell shrinkage in a hypertonic solution 60. Hemolysis, red blood cell bursting in a hypotonic solution 61. Isotonicity importance, critical for injectables, ophthalmic, nasal, and irrigation solutions. Also, freezing point depression method, technique to calculate solution tonicity 63. NaCl equivalent method, method to adjust tonicity in pharmaceutical system 64. Isotonic solution, solution with equal osmotic pressure to body fluid 65. Freezing point depression method, calculates isotonicity by freezing point change 66. Sodium chloride equivalent method, determines isotonicity based on NaCl equivalent weight 67. TF, change in freezing point caused by a solution 68. E-value, weight of NaCl per 1 gram of substance 69. Adsorption, accumulation of molecules at an interface 70. Absorption, penetration of absorbing material by absorbed substances 71. Free energy, state of energy in a system available to do work 72. Adsorption of gases, displacement of air by another gas 73. Adsorption from solution, displacement of solvent molecules by a more strongly adsorbed solute 74. Solid-gas interface, boundary between a solid surface and gas phase 75. Physical adsorption, weak attractions like gas condensation 76. Chemisorption, chemical reaction at the surface 77. Reversibility, ability to remove adsorbate easily 78. Effect of temperature, temperature impact on adsorption amount 79. Monolayer, single layer adsorption at low pressure 80. Adsorption isotherms, relationship between adsorption amount, adsorbent mass, and gas pressure 81. Freundlich equation, relates adsorption amount to equilibrium pressure 82. Type I adsorption isotherm, monolayer adsorption followed by saturation 83. Type II adsorption isotherm, sigmoidal shape indicating multi-layer formation 84. Adsorption from solution, solute adhesion from a liquid solution 85. Selective adsorption, preferential adsorption of specific solutes 86. Van der Waals forces, weak intermolecular forces in physical adsorption 1. Desorption, reverse of adsorption, based on similar principles 2. Ionic solutes, substances that may be desorbed by pH changes 3. Saponin, strongly adsorbed substance used to displace materials 4. Decolorization, process using charcoal to obtain colorless solutions 5. Water vapor adsorption, alumina and silica gel adsorb up to 40% water 6. Kaolin, adsorbs intestinal toxins by ion exchange 7. Activated charcoal, emergency antidote for alkaloid poisoning 8. Adsorption chromatography, separation technique based on adsorbent affinity 9. Surface area determination, method to measure specific surface area 10. Non-specific adsorption, adsorption of drugs, nutrients, and enzymes 11. Contact angle, angle indicating wetting problems. Some content was made using AI in the realm of pharmaceuticals, where compounds are keen. Here's a mnemonic verse, to remember what each term means. Thermodynamics, the very first step, energy in motion, its secrets adept. Kinetics follows, with rates so profound, the speed of diffusion, where answers are found. Passive and facilitated, transport types 2, moving molecules, with or without a Q. Actives the third, against the gradient it fights, transporting molecules to unprecedented heights. Fick's laws, first and second, guiding diffusion's rate, mathematical models that scientists appreciate. Lag and burst effects, in delivery they play a part, controlling drug release, they're an essential art. Brownian motion, particles in a dance, random movements in fluid, given a chance. Equilibrium's balance, no gradient in sight, where concentrations level, everything's just right. Osmosis, pinocytosis, processes so neat, moving water and engulfing, they never admit defeat. Endocytosis and phagocytosis, cellular intake, engulfing solids and large particles, for the cell's own sake. Diffusion coefficient, a measure to know how permeable a molecule, how easily it will flow. Partition and permeability, coefficients of their own, describing how drugs through membranes are shown. Zero-order processes, constant and sure, a steady rate of transport, continuously pure. Transdermal patches, inverted models, quite the sight, for studying absorption, they bring much insight. Reservoirs and matrix systems, controlled release they ensure, with Fick's law governing, their effect is pure. Ethyl cellulose membranes, diffusional systems to heat, cutting them is risky, toxicity could proceed. Drug diffusion and absorption, key processes in play, with dissolution steps, leading the way. Controlled and sustained formulations, designed with care, for slow drug release, absorption control to spare. Molecular weight, paracellular paths, influence absorption, guiding pharmacokinetics graphs. Transcellular routes, and the pH partition hypothesis, predicting drug penetration, a scientific synthesis. Chemical equilibrium, Brønsted-Lowry's guide, with ionization, and the law of mass action by its side. Specific rates, dissociation constants, to understand, the ionization of weak acids, in water's hand. Ka and Kb, constants of ionization, defining acids, and bases, in aqueous solution. The pH scale and isotonicity, parameters to measure, for solutions' effects on cells, and their pressure. Freezing point depression, NaCl's equivalent role, in adjusting tonicity, they take control. Adsorption and absorption, processes defined, with free energy and adsorption of gases, intertwined. Physical and chemisorption, adsorption's two faces, with reversibility and temperatures traces monolayers and isotherms, adsorption to discern, Freundlich's equation, and isotherm types to learn. Desorption, ionic solutes, and saponins might, in displacing materials, they show their fight. Decolorization and water vapor adsorption's role, in creating clearer solutions, they take their toll. Kaolin and activated charcoal, adsorbents so grand, in emergencies and toxin removal, they lend a hand. Adsorption chromatography, a separation technique, with surface area determination, the specifics we seek. Nonspecific adsorption, contact angles clue, in preparations of suspensions and emulsions. 2. Neosomal formulations, antacids relief, taste masking and adsorption of water, beyond belief. Micromeritics, the study of small, particle size and porosity, they cover it all. Flow properties, angle of repose, in powders and granules, how stability shows. Bulkiness and particle size, characteristics defined, in drug design and delivery, they're intertwined. Monodisperse powders, uniformity's key, for consistency in therapy, as clear as can be. In pharmaceuticals, where precision's the norm, this mnemonic poem helps knowledge transform. Continuing the adventure, absorption and adsorption at the Library of Congress, D.C. The following week, Professor Avery surprises her students with an unexpected visit to the majestic Library of Congress. Amidst the vast collection of knowledge, they meet two new characters, Ada the absorber and Alex the adsorber. Ada, with her gentle touch, demonstrates how materials can be incorporated into the bulk phase, similar to how a sponge absorbs water. Alex, on the other hand, shows how substances can adhere to surfaces, likening it to how dust collects on the shelves of the library. As they explore the library, the students are challenged to differentiate between adsorption and absorption by examining various historical documents and artifacts, seeing firsthand how some materials have absorbed ink over time while others have surface-level deposits. This interactive session deepens their understanding of the two processes, emphasizing their importance in drug formulation and delivery. Chapter 7, Chemical Equilibrium at the National Gallery of Art, DC. The journey continues to the National Gallery of Art, where the balance between art and space mirrors the concept of chemical equilibrium in pharmaceuticals. Here, the students are introduced to Ellie the equilibrist, who balances paint on her palette, constantly shifting but maintaining a harmonious composition. Through interactive art installations, the students visualize how reactants and products in a chemical reaction reach a state of balance, akin to the dynamic yet steady state of equilibrium in chemical reactions. Using the art around them, the students participate in activities that simulate reversible reactions, understanding how changes in conditions can shift the equilibrium, much like how an artist adjusts a composition to achieve the desired effect. Chapter 8, Ionization and pH at the National Museum of Natural History, DC. At the National Museum of Natural History, the group delves into the world of ionization and pH, crucial for understanding drug solubility and absorption. They meet Isaac the ionizer and Paige the pH specialist, who guide them through interactive exhibits of minerals and gemstones, demonstrating ionization in action. Paige leads an experiment with litmus paper and various solutions, illustrating how pH affects ionization, while Isaac explains the relevance of the Henderson-Hasselbalch equation in predicting drug ionization states. This hands-on approach helps students grasp the complexities of drug formulation and its dependency on pH levels. Chapter 9, Drug Absorption and Solubility at the United States National Arboretum, DC. The serene environment of the United States National Arboretum sets the stage for understanding drug absorption and solubility. Surrounded by diverse plant species, the students learn from Sol the solubilizer about how the solubility of substances is crucial for their absorption into the body, similar to how water-soluble nutrients are absorbed by plants. Through a series of experiments with plant cuttings and various solvents, the students observe how solubility affects absorption rates, drawing parallels to pharmaceutical applications and the significance of designing drugs with optimal solubility for effective absorption. Epilogue, Reflections at the Reflecting Pool, DC. The educational journey culminates at the iconic reflecting pool, where the reflections of the monuments serve as a metaphor for the students' introspection on their learning journey. Professor Avery encourages each student to share their most impactful memory from the adventure, reinforcing the lessons learned. As they share stories of Theo, Kim, Ada, Alex, and the others, the students realize that the principles of adsorption are not just abstract concepts but are intertwined with the world around them, from the art they admire to the natural environment they cherish. This story-based learning adventure, rich with characters and interactive experiences, ensures that the complex principles of adsorption in pharmaceuticals are not only understood but are also vividly remembered and appreciated. As the sun dipped lower in the sky, casting long shadows across the reflecting pool, the students gathered around, their minds buzzing with the day's lessons. Professor Avery, seeing their enthusiasm, decided to delve deeper into the complexities of pharmaceutical adsorption with a final, impromptu session. Chapter 10, Surface Area and Adsorption at the Hubble Space Telescope Display, Smithsonian National Air and Space Museum. Under the dim lights of the museum, the group congregated around the awe-inspiring display of the Hubble Space Telescope. Professor Avery introduced them to Sarah the surface analyst, a character who explained the pivotal role of surface area in adsorption, much like the vast mirrors of the Hubble telescope capturing the faintest light from distant galaxies. Imagine each molecule as a tiny star, Sarah began, and the adsorbent surface as our telescope's mirror. Just as a larger mirror captures more light, a greater surface area allows for more extensive adsorption. The students, drawing a parallel, understood how maximizing the surface area of an adsorbent in pharmaceutical formulations could enhance the drug's efficacy, similar to how the telescope's large aperture gathers more celestial information. Chapter 11, Adsorption Isotherms. At the Franklin Delano Roosevelt Memorial. As twilight approached, the group made their way to the serene setting of the Franklin Delano Roosevelt Memorial, with its cascading waterfalls and quiet alcoves. Here, they met Yvonne the isotherm, who used the memorial's landscape to illustrate the concept of adsorption isotherms. With each step you take through this memorial, think of it as increasing pressure in an adsorption system, Yvonne explained. Initially, you'll notice a rapid increase in adsorption, much like the quick uptake of the serene atmosphere. But as you continue, the effect becomes less pronounced, approaching a plateau. This simile helped the students visualize how, at low pressures, adsorbents fill the most accessible adsorption sites rapidly, akin to how one first absorbs the tranquility of the memorial. As pressure increases, additional adsorption occurs at a diminishing rate until reaching saturation, paralleling the memorial's calming effect, plateauing as one becomes accustomed to the ambience. Chapter 12, Kinetics of Adsorption. At the National World War II Memorial. The day's final lesson took place at the National World War II Memorial, its fountains and pillars aglow under the night sky. The character for the setting was Kay the kineticist, who drew comparisons between the movement of water through the memorial's fountains and the kinetics of adsorption. Notice how the water's flow varies, Kay pointed out, from rapid cascades to gentle ripples. This variability mirrors the kinetics of adsorption, where the rate at which a substance adheres to a surface can range from immediate to gradual, influenced by factors like concentration gradients and temperature. The students likened the initial rush of water in the fountains to fast adsorption rates at high concentrations, while the slow, meandering trickles resembled the reduced adsorption rates as equilibrium approached, offering a tangible understanding of kinetic principles. Reflections and farewells. At the reflecting pool. Gathered once more by the reflecting pool, the students reflected on their journey. The monuments and memorials, once mere historical landmarks, had become vivid illustrations of complex scientific principles. The stories of Theo, Kim, Ada, Alex, Sarah, Yvonne, and Kay would linger in their minds, anchoring the intricate concepts of pharmaceutical adsorption to tangible, memorable experiences. Professor Avery smiled, satisfied with the day's achievements. You've seen how science intersects with the world around us, from the vast reaches of space captured by the Hubble telescope to the serene waters of our memorials. Carry these lessons forward, and may your understanding of adsorption be as deep and enduring as the impressions left by today's journey. As the group disbanded, the reflecting pool's still waters mirrored the Lincoln Memorial, a silent witness to their day of learning, a metaphor for the clarity and depth of understanding they now possessed. The principles of adsorption, once abstract and elusive, had been rendered clear and tangible, much like the reflections on the water's surface. Adsorption principles in pharmaceuticals. 1. Thermodynamics, study of energy and its transformations in diffusion. 2. Kinetics, study of the rate of diffusion processes. 3. Passive transport, movement of molecules without energy input. 4. Facilitated transport, movement of molecules with the aid of a carrier. 5. Active transport, movement of molecules against a concentration gradient. 6. Fick's law of diffusion, mathematical model describing the rate of diffusion. 7. Lag time effect, delay in drug diffusion from a delivery device. 8. Burst effect, sudden release of a large amount of drug from a device. 9. Brownian motion, random movement of particles in a fluid. 10. Equilibrium, state where no concentration gradient exists. 11. Osmosis, movement of solvent, usually water, across a membrane. 12. Pinocytosis, cellular process of engulfing fluids. 13. Endocytosis, cellular process of engulfing solids. 14. Phagocytosis, cellular process of engulfing large particles. 15. Diffusion coefficient, measure of molecule permeability in cm2/S16. Fick's first law, J equals ddc/dx, shows flux proportional to concentration gradient 17. Fick's second law, dm/dt equals ds, dc/dx, relates concentration gradient to transport rate 18. Partition coefficient, relates drug concentrations in membrane to compartments 19. Sink conditions, state where CR is nearly zero, no drug accumulation 20. Permeability coefficient, P equals dk/h, measures membrane permeability in cm/S21. Zero order process, constant rate transport, slope equals PSCD22. Transdermal patch, delivery system for zero order drug transport 23. Inverted closed loop intestinal model, used to study oral drug absorption 24. Lag time, delay before drug release in controlled systems 25. Burst effects, non-constant drug release from controlled systems 26. Lag time effect, time for drug to saturate tissue before absorption 27. Burst effect, rapid release from presaturated membranes 28. Diffusion, main force for drug release in sustained release products 29. Reservoir systems, devices with drug core surrounded by rate controlling membrane 30. Matrix systems, drug dispersed evenly in a matrix for slow release 31. Fick's law, governs release from reservoir systems, enabling zero order release 32. Dose dumping, instantaneous release of excess drug from reservoir system 33. Ethyl cellulose, commonly used for rate limiting membrane in oral formulations 34. Diffusional reservoir systems, should not be cut, broken, or chewed to avoid toxicity 1/3 Adsorption principles in pharmaceutical study online at https://quizlet.com/_EO51M35. Drug diffusion, occurs through rate controlling membrane for systemic delivery 36. Drug absorption, occurs by diffusion in gastrointestinal tract and other sites 37. Dissolution step, rate limiting step for drug absorption of low aqueous solubility drugs 38. Partition coefficient, factor governing drug absorption in gastrointestinal tract 39. Controlled and sustained release formulations, designed to release drugs slowly for absorption control 40. Molecular weight, affects drug absorption, high weight compounds may not be absorbed 41. Paracellular transport, drug movement between cells by convection 42. Transcellular route, drug transport through cells by diffusion 43. pH partition hypothesis, suggests drugs penetrate membranes in unionized form based on pH 44. Henderson-Hasselbalch equation, relates pH, pKa, and drug ionization for absorption prediction 45. Chemical equilibrium, dynamic balance in reactions with constant reactant/product concentrations 46. Brønsted-Lowry theory, defines acids as proton donors and bases as proton acceptors 47. Ionization of weak electrolyte, Brønsted-Lowry representation of weak acid ionization in water 48. Law of mass action, states rate of forward reaction is proportional to reactant concentration 49. Specific reaction rates, proportionality constants in forward and reverse reactions 50. Dissociation constant, constant for weak acid ionization, denoted as Ca 51. Dissociation constant, constant for weak acid ionization, denoted as Ca 52. Ca, ionization constant for weak acids, equals H3O plus A/Ha53. General form of equation, representation of weak acid ionization, Ha plus H2O. H3O plus A54. Kb, ionization constant for weak bases, equals OBH plus /B55. Kw, dissociation constant of water, equals 1x1014 at 250C56. pH scale, Sorensen's scale, defined as log H3O plus 57. Isotonic solution, solution with equal osmotic pressure to another solution 58. Tonicity, Effect of a solution on cell shape due to osmotic pressure 59. Crenation, red blood cell shrinkage in a hypertonic solution 60. Hemolysis, red blood cell bursting in a hypotonic solution 61. Isotonicity importance, critical for injectables, ophthalmic, nasal, and irrigation solutions. Also, freezing point depression method, technique to calculate solution tonicity 63. NaCl equivalent method, method to adjust tonicity in pharmaceutical system 64. Isotonic solution, solution with equal osmotic pressure to body fluid 65. Freezing point depression method, calculates isotonicity by freezing point change 66. Sodium chloride equivalent method, determines isotonicity based on NaCl equivalent weight 67. TF, change in freezing point caused by a solution 68. E-value, weight of NaCl per 1 gram of substance 69. Adsorption, accumulation of molecules at an interface 70. Absorption, penetration of absorbing material by absorbed substances 71. Free energy, state of energy in a system available to do work 72. Adsorption of gases, displacement of air by another gas 73. Adsorption from solution, displacement of solvent molecules by a more strongly adsorbed solute 74. Solid-gas interface, boundary between a solid surface and gas phase 75. Physical adsorption, weak attractions like gas condensation 76. Chemisorption, chemical reaction at the surface 77. Reversibility, ability to remove adsorbate easily 78. Effect of temperature, temperature impact on adsorption amount 79. Monolayer, single layer adsorption at low pressure 80. Adsorption isotherms, relationship between adsorption amount, adsorbent mass, and gas pressure 81. Freundlich equation, relates adsorption amount to equilibrium pressure 82. Type I adsorption isotherm, monolayer adsorption followed by saturation 83. Type II adsorption isotherm, sigmoidal shape indicating multi-layer formation 84. Adsorption from solution, solute adhesion from a liquid solution 85. Selective adsorption, preferential adsorption of specific solutes 86. Van der Waals forces, weak intermolecular forces in physical adsorption 1. Desorption, reverse of adsorption, based on similar principles 2. Ionic solutes, substances that may be desorbed by pH changes 3. Saponin, strongly adsorbed substance used to displace materials 4. Decolorization, process using charcoal to obtain colorless solutions 5. Water vapor adsorption, alumina and silica gel adsorb up to 40% water 6. Kaolin, adsorbs intestinal toxins by ion exchange 7. Activated charcoal, emergency antidote for alkaloid poisoning 8. Adsorption chromatography, separation technique based on adsorbent affinity 9. Surface area determination, method to measure specific surface area 10. Non-specific adsorption, adsorption of drugs, nutrients, and enzymes 11. Contact angle, angle indicating wetting problems under the starlit sky, the reflecting pool's tranquil waters served as a perfect canvas for reflection and deeper understanding. Seizing the moment of collective curiosity and inspired engagement, Professor Avery decided to extend the lecture into the night, delving into more nuanced aspects of adsorption with precise technical language and advanced concepts. Chapter 13, Chemisorption and Physisorption at the United States Capitol. The group's next stop was the illuminated United States Capitol, a symbol of decision-making and commitment, mirroring the irreversible nature of chemisorption. Professor Avery introduced them to Charles the Chemisorber, a character who explained the concept of chemisorption with its strong, specific, and often irreversible binding, akin to the laws enacted within the Capitol that strongly bind citizens. Chemisorption, Charles elucidated, involves the formation of chemical bonds between the adsorbate and the surface. It's akin to the legislative process, where decisions, once passed, are not easily reversed, and the bond between the law and the people is robust and enduring. This analogy helped the students grasp the permanence and specificity of chemisorption in contrast to physisorption, which, like a visitor's fleeting impression of the capital's grandeur, is characterized by weaker, non-specific van der Waals forces and is reversible. Chapter 14, Langmuir and Freundlich isotherms. At the Library of Congress. With minds eager for more, the students reconvened at the Library of Congress, surrounded by centuries of knowledge and wisdom. Here, they met Laura the Langmuir expert and Freddie the Freundlich scholar, who used the vast collection of books to illustrate the concepts of Langmuir and Freundlich adsorption isotherms. Laura explained the Langmuir isotherm, which assumes monolayer adsorption onto a surface with a finite number of identical sites, akin to a library with a limited number of identical reading desks, each capable of accommodating only one reader at a time. Conversely, Freddie introduced the Freundlich isotherm, suitable for heterogeneous surfaces and multi-layer adsorption, likened to the library's various reading areas, each offering different seating arrangements and capacities, accommodating multiple readers in layers. This setting provided a vivid illustration of the two isotherms, enhancing the students' understanding of how different surfaces and adsorbate concentrations influence adsorption behavior. Chapter 15, Adsorption Kinetics and Mechanisms. At the Hirshhorn Museum. The final lesson took place at the Hirshhorn Museum, its modern art installations reflecting the complexity and diversity of adsorption mechanisms. Professor Avery, with the help of kinetic models and dynamic sculptures, illustrated the steps involved in adsorption kinetics: transport to the adsorbent surface, adsorption onto the surface sites, and in some cases, diffusion into the pores of the adsorbent material. Using the art piece's movement and the interplay of light and shadow, she explained how these steps are influenced by various factors, including the physicochemical properties of the adsorbate, the adsorbent's surface characteristics, and the surrounding conditions, such as temperature and pressure. This immersive experience helped the students visualize the dynamic and multifaceted nature of adsorption kinetics, likening each step to a phase in an art installation's life cycle, from conception and installation to the viewer's engagement with the piece. Reflections and conclusions by the reflecting pool. Gathered once again by the serene reflecting pool, the students shared their insights and reflections, their minds alight with newfound knowledge. Professor Avery commended their curiosity and engagement, emphasizing the importance of understanding adsorption's fundamental principles and applications in pharmaceuticals and beyond. As the evening drew to a close, the reflecting pool's calm waters mirrored the clear, deepened understanding within each student. The journey through Washington D.C.'s landmarks had transformed abstract scientific concepts into vivid, memorable experiences, embedding the principles of adsorption into their minds as indelibly as the monuments stood etched against the night sky. As the nocturnal symphony of Washington, D.C. reached its crescendo, with the gentle hum of the city under the starry sky, Professor Avery and her students congregated for one last time by the reflecting pool. The waters, calm and reflective, seemed to hold within them the multitude of concepts explored, now clear and vivid in the students' minds. With a sense of accomplishment and a touch of nostalgia for the day's end, Professor Avery decided to conclude the session in a unique and memorable manner, through acrostics, weaving together the key terms and concepts they had journeyed through. Thermodynamics: transformations of energy, vast and grand, heat and work, in nature's hand, entropy's dance, intricate and free, reactions and changes, as constant as the sea, matter's movements, from solid to air, order to disorder, everywhere, driving forces, unseen yet clear, yielding processes, far and near, nature's laws, in every reaction, adsorption's role, a key fraction, molecular interactions, a subtle art, in every phase, they play their part, cycles of energy, endlessly spun, science's quest, never done. Kinetics: keenly observing, rates so diverse, in every reaction, a universe, nature's clock, ticking unseen, every molecule, in motion keen, time's passage, in reactions felt, interactions swift, bonds to melt, catalysts speeding, the dance of fate, science deciphers, as mysteries abate. Adsorption attachment at surfaces, a dance so fine, diverse molecules, in interaction align, specific and strong, or weak and broad, on solids and liquids, they come aboard, reversible or not, the bond's the key, physical or chemical, what will it be? Temperature and pressure, their roles play, isotherms mapping, the adsorbate's way, optimizing use, in filters and drugs, nature and science, giving us hugs. With each acrostic recited, the concepts they had explored throughout the day were etched deeper into the students' memories, intertwining with the visuals of the landmarks and the stories of characters they had met. The reflecting pool, witness to their intellectual voyage, shimmered with the reflections of the monuments, a testament to the journey of discovery they had undertaken. As the night deepened and the moment to part ways arrived, Professor Avery offered her final words, "May the principles of adsorption, much like the memories we've created today, find a firm place to adhere in your minds and careers. Let the journey continue beyond today, in labs, in classrooms, and in the ever-unfolding story of science." With heartfelt farewells and the promise of future explorations, the students dispersed into the night, their minds alight with knowledge and their hearts filled with the unforgettable adventure through the landmarks of Washington, D.C., now forever linked to the fascinating world of adsorption in pharmaceuticals. Purpose of these episode: these are not at all for medical advice or suggestions, we disclaim any loss in any way. These episodes are for educational purposes only, and are not for medical advice or suggestions. The views of this podcast represent those of my guest, S, and I.
Welcome to the New Student Pharmacist podcast, the podcast series, The New Student Pharmacist, where we discuss chemistry and pharmacy, as well as leaders in pharmacy careers, community, and chemistry and pharmacy research. We look forward to your subscriptions to support the work we are doing and follow us on Spotify and Apple Podcasts. Note, the views on the podcast represent those of my guest and I. We encourage you to subscribe on Spotify and Apple Podcasts.
300 drugs. Brand / generic / class / indication 1. Lortab, hydrocodone / acetaminophen pain 2. Vicodin, hydrocodone / acetaminophen pain 3. Lorcet, hydrocodone / acetaminophen pain 4. Norco, hydrocodone / acetaminophen pain 5. Synthroid, levothyroxine T4 hypothyroidism 6. Levoxyl, levothyroxine T4 hypothyroidism 7. Levothyroid, levothyroxine T4 hypothyroidism 8. Prinavil, lisinopril ACE hypertension / proteinuria 9. Zestril, lisinopril ACE hypertension / proteinuria 10. Xanax, alprazolam benzo anxiety 11. Fortamit, metformin biguanide diabetes 12. Glumetza, metformin biguanide diabetes 13. Glucophage, metformin biguanide diabetes 1 / 29. Top 300 drugs. Brand / generic / class / indication 14. Lasix, furosemide loop diuretic hypertension / edema 15. Preluzec, omeprazole PPI GERD 16. Zocor, simvastatin HGM-CoA reductase inhibitor dyslipidemia 17. Livalo, pitavastatin HGM-CoA reductase inhibitor dyslipidemia 18. And Skol, fluvastatin HGM-CoA reductase inhibitor dyslipidemia, take at bedtime, 19. Lipita, atorvastatin HGM-CoA reductase inhibitor dyslipidemia 20. Norfasc, amlodipine DHP calcium channel blocker hypertension 21. Proventil, albuterol short-acting beta agonist rescue inhaler 22. Ventolin, albuterol short-acting beta-agonist rescue inhaler 23. Pro-Air, albuterol short-acting beta-agonist rescue inhaler 24. Ambien, zolpidem imidazopyridine sleep 25. Celexa, citalopram SRI anxiety / depression 2 / 29 top 300 drugs, brand / generic / class / indication 26. Hydrodiuryl, hydrochlorothiazide thiazide diuretic hypertension 27. Neurontin, gabapentin GABA analog nerve pain, epilepsy 28. Zantac, ranitidine H2 rugged 29. Ultram, tramadol central acting analgesic pain 30. Bayers, aspirin said pain / inflammation / antiplatelet 31. Ecatrin, aspirin said pain / inflammation / antiplatelet 32. Cadia, potassium supplement potassium low potassium 33. Clocon, potassium supplement potassium low potassium 34. Clonopin, clonazepam benzo anxiety / depression 35. Coumadin, warfarin anticoagulant 36. Jantoven, warfarin anticoagulant 37. Singulair, montelukast oral nicotriene receptor antagonist asthma / respiratory / also seasonal allergic rhinitis 38. Laprasa, metoprolol tartrate selective BB hypertension / HF3 / 29 top 300 drugs, brand / generic / class / indication 39. Ambrx, cyclobenzaprine muscle relaxer 40. Flecaryl, cyclobenzaprine muscle relaxer 41. Fexmid, cyclobenzaprine muscle relaxer 42. Seroquel, quetiapine fumarate atypical antipsychotics schizophrenia / bipolar 43. Plavix, clopidogrel antiplatelet stroke prevention 44. Oxycontin, oxycodone opioid pain 45. Decile, trazodone tetracyclic antidepressant labeled for depression but usually sedative off-label 46. Coreg, carvedilol 47. Mevaca, lovastatin HMO-CoA reductase inhibitor dyslipidemia 48. Zoloft, sertraline SSRI anxiety / depression 49. Cymbalta, duloxetine SNRI anxiety / depression 50. Percocet, roxicet, Endocet, oxycodone / acetaminophen CII opioid pain 51. Advair, fluticasone propionate / salmeterol zinarfote bronchodilator asthma /COPD 4 / 29 top 300 drugs, brand / generic / class / indication 52. Lantus, insulin glargine, rDNA origin, insulin diabetes 53. Tuyo, insulin glargine, rDNA origin, insulin diabetes ** 300 unit / ml ** 54. Simlin pen, pramlintide analog of amylin hormone diabetes ** do not give if skip a meal ** 55. Tarprul XL, metoprolol succinate cardioselective BBHTN 56. Zebieta, bisoprolol 57. Zithromax, Zmix, azithromycin macrolide bacterial infections 58. Prozac, fluoxetine SSRI anxiety / depression 59. Effega, venlafaxine SNRI anxiety / depression / nerve pain 60. Tenormin, atenolol cardioselective BBHTN 61. Elaval, amitriptyline SNRI anxiety/depression/nerve pain 62. Combivant, ipratropium bromide /albuterol sulfate, MDI, COPD, asthma 63. Wellbutrin, bupropion norepinephrine dopamine reuptake inhibitor antidepressant /smoking aid 64. Zibin, bupropion norepinephrine dopamine reuptake inhibitor antidepressant /smoking aid 5 /29 top 300 drugs. Brand /generic /class /indication 65. Nexium, esomeprazole PPI GERD 66. Ativan, lorazepam benzo anxiety /panic attacks 67. Trisa, phenofibrate dyslipidemia /triglycerides *** take with food cc *** 68. Lexapro, escitalopram SSRI anxiety /depression 69. Flonase, fluticasone propionate nasal corticosteroid nasal congestion 70. Deltasone, prednisone steroid inflammation /allergy /immunosuppression 71. Depakote, Devalpro valproic acid seizure /bipolar 72. Catapraz, clonidine alpha agonist hypertension /sedative /ADHD 73. Aldome, methyldopar alpha agonist hypertension 74. Cardizem, diltiazem CCBHTN and angina 75. Karsha, diltiazem 76. Tiazic, diltiazem CCBHTN and angina 6 /29 top 300 drugs. Brand /generic /class /indication 77. Soma, carisoprodol carbamate muscle relaxer 78. Risperdal, risperidone atypical antipsychotic schizophrenia /antipsychotic 79. Mobic, meloxicam said anti-inflammatory 80. Detrol, toltrodine cholinergic incontinence 81. Topamax, topiramate anticonvulsant seizure /nerve pain 82. Martrin, ibuprofen said pain /inflammation 83. Amoxil, amoxicillin trihydrate penicillin bacterial infection 84. Trimox, amoxicillin trihydrate penicillin bacterial infection 85. Moxatag, amoxicillin trihydrate penicillin bacterial infection 86. Naproxen, naproxen 87. Zestoretic, lisinopril /hydrochlorothiazidase inhibitor and thiazide diuretic HTN 88. Prinzide, lisinopril /hydrochlorothiazidase inhibitor and thiazide diuretic HTN 89. Reglan, metoclopramide prokinetic nasio /GERD 7 /29 top 300 drugs. Brand /generic /class /indication 90. Bactrim, sulfamethoxazole /trimethoprim sulfur antibiotic bacterial infection 91. Septra, sulfamethoxazole /trimethoprim sulfur antibiotic bacterial infection 92. Actose, pioglitazone thiazolidinedians diabetes 93. Abilify, aripiprazole atypical antipsychotic schizophrenia /antipsychotic 94. Fosamax, alendronate bisphosphonate osteoporosis 95. Spiriva, shiotropium bromide inhalation bronchodilator COPD 96. Flomax, tamsulosin alpha blocker BPH 97. Lyrica, pregabalin anticonvulsant nerve pain 98. Micronase, glyburide sulfonyrua diabetes 99. Diabeta, glyburide sulfonyrua diabetes 100. Aricept, donepezylcholinesterase inhibitor Alzheimer's 101. Cresta, rosuvastatin HGMO co-reductase inhibitor dyslipidemia 102. Valium, diazepam benzo anxiety / panic attacks 8 / 29 top 300 drugs, brand / generic / class / indication 103. Aldactone, spironolactone potassium sparing diuretic HF, HTN 104. Inspra, eplerenone potassium sparing diuretic HF, HTN 105. Bistolic, nebivolol 106. Tecturna, aliskiren plus HCTZ 107. Valterna, aliskiren and valsartan 108. Protonix, pantoprazole 109. Lamictal, lamorigine antipyletic seizure 110. Xopnex, levolbuterol labor asthma / COPD 111. Glucotrol, glucotrol XL, glipizide sulf diabetes 112. Allegra, fexufenadine antihistamine hives itching allergy 113. Pravacol, pravastatin HGMO co-reductase dyslipidemia 114. Premarin, estrogens conjugated cream estrogen menopause 115. Imda, ismo, isosorbide mononitrate nitrate angina, HTN 116. Monoke, isosorbide mononitrate nitrate angina, HTN 9 / 29 top 300 drugs, brand / generic / class / indication 117. Izordil, dilatrate, isosorbide dinonitrate nitrate angina, HTN 118. Cipro, ciprofloxacin fluoroquinolone bacterial infection 119. Dizide, trienterine / hydrochlorothiazide diuretic HTN 120. Maxazide, trienterine / hydrochlorothiazide diuretic HTN 121. Fnagan, promethazine antihistamine allergies, pain, nausea 122. Xyloprim, allopurinol xanthine oxidase inhibitors gout 123. Nitrostat, nitroglycerin nitrates angina 124. Nitroquick, nitroglycerin nitrates angina 125. Prevacid, lansoprazole PPI GERD 126. Paxil, paroxetine SSRI anxiety / depression 127. Pexiva, paroxetine SSRI anxiety / depression 128. Vibramycin, doxycycline hiclate tetracycline antibiotics bacterial infection 129. Vibratabs, doxycycline hiclate tetracycline antibiotics bacterial infection 10 / 29 top 300 drugs, brand / generic / class / indication 130. Adra, amphetamine / dextroamphetamine salts CII amphetamine ADHD 131. Novolog, insulin aspart, rDNA origin insulin diabetes 132. Namenda, memantine NMDA receptor blocker Alzheimer's 133. Duragesic, fentanyl transdermal opioid chronic pain 134. Remeron, mirtazepine SNRI anxiety / depression 135. Zetia, ezetimibe cholesterol absorption inhibitor dyslipidemia 136. Celebrex, celecoxib said pain / inflammation 137. Diovan, valsartan angiotensin reductase inhibitor HTN 138. Atarax, hydroxyzine HCl, OTC, antihistamine sleep, itching allergy, anxiety 139. Unizorm, doxylamine antihistamine sleep 140. Inderal, propranolol non-selective BB hypertension /HF 141. Brevibloc, esmolol 142. Inopran XL, propranolol non-selective BB hypertension /HF 11/29 top 300 drugs, brand /generic /class /indication 143. Lanoxin, digoxin cardiac glycoside arrhythmia and HF 144. Lanoxicaps, digoxin cardiac glycoside arrhythmia and HF 145. Digitc, digoxin cardiac glycoside arrhythmia and HF 146. Dristol, vitamin D2, ergocalciferol inactive vitamin D bone health 147. Roquetrol, vitamin D3, calcitriol active vitamin D bone health 148. Amaryl, glympyride sulfura diabetes 149. Prandin, ripaglinide mglytinids rapid acting glinids 150. Starlix, nateglinide mglytinids rapid acting glinids 151. Vitarin, ezetimibe /simvastatin cholesterol absorption inhibitor plus HGMO cholesterol 152. Folate, folic acid deficiency /megaloblastic anemia 153. Folacin, folic acid B vitamin folic acid deficiency /megaloblastic anemia 154. Troylglutamine acid, folic acid B vitamin folic acid deficiency /megaloblastic anemia 155. Kiflex, cefalexin monohydrate cef antibiotic bacterial infection 12/29 top 300 drugs, brand /generic class /indication 156. Vazotc, enalapril maleate ACEHTN 157. Buspa, buspionazapirone anxiety 158. Tegretol, carbamazepine antiepileptic seizure /nerve pain 159. Carbatrol, carbamazepine antiepileptic seizure /nerve pain 160. Equetrol, carbamazepine antiepileptic seizure /nerve pain 161. Cozar, losartan potassium ARBHTN 162. Ritalin, methylene, metadate, methylphenidate phenethylamine and piperidine ADHD 163. Ditropin, oxybutynine chloride, oral, antispasmodic overactive bladder 164. Mescontin, morphine sulfate extended release opioid pain 165. Slow Fe, ferrous sulfate iron anemia 166. Lidodom, lidocaine transdermalamide local anesthetic pain for local area 167. Nefex, iron polysaccharide iron anemia 168. Cineme, carbidopar /levodopa dopaminergic agent Parkinson's 13/29 top 300 drugs, brand /generic class /indication 169. Duopa, carbidopar /levodopa dopaminergic agent enteral suspension 170. Ritari, carbidopar /levodopa dopaminergic agent cap 171. Stalevo, lavadopar /carbidopar and entacapone, Contan, 172. Zenaflex, tizonidine centrally acting ±2 adrenergic agonist muscle spasms muscle relaxant 173. Lioresal, Baclofen muscle relaxant 174. Isoptin, verapamil non-DHPCCBHTN, angina 175. Calan, verapamil non-DHPCCBHTN, angina 176. Vrilin, verapamil non-DHPCCBHTN, angina 177. Requip, ropinirole dopamine agonist Parkinson's 178. Scalaxin, metaxalone muscle relaxer, pain 179. Restoral, temazepam benzo anxiety 180. Bentyl, dicyclomine gut antispasmodic IBS 181. Cerex, oxazepam benzo anxiety 14/29 top 300 drugs, brand /generic /class /indication 182. Visterol, hydroxyzine pamoate antihistamine anxiety, itching 183. Dilantin, phenytoin sodium extended anticonvulsant seizure 184. Capsules, phenytoin sodium extended anticonvulsant seizure 185. Diovan HCT, valsartan /hydrochlorothiazide ARB plus thiazide HTN 186. Diflucan, fluconazole antifungal 187. Humulin, insulin diabetes 188. Flovent, fluticasone propionate inhalation steroid and decongestant 189. Lateral, amlodipine /benazepril 190. Exforge, amlodipine /valsartan CCB /ARBHTN 191. Aza, amlodipine /omasartan CCB /ARBHTN 192. Phenarphine with codeine, acetaminophen /codeine pain 193. Tylenol -3, acetaminophen /codeine pain 194. Trileptal, oxcarbazepine anticonvulsant seizure 195. Lithianate, lithium carbonate mood stabilizer bipolar disorder 15/29 top 300 drugs, brand /generic /class /indication 196. Lithotabs, lithium carbonate mood stabilizer bipolar disorder 197. Lithobid, lithium carbonate mood stabilizer bipolar disorder 198. Mirapex, pramipexole dihydrochloride dopamine agonist Parkinson's and restless leg 199. Nistap, nystatin topical antifungal fungal infection 200. Nasonex, mometazone furoate monohydrate intranasal nasal congestion /allergic rhinitis 201. Augmentin, amoxicillin /clavulinate potassium bacterial infection 202. Estrase, estradiol menopause 203. Latensin, benazepril ACEHTN 204. Tesalorm, benzoatate antitussive cough 205. Kenalog, triamaquinolone acetonide topical corticosteroid itching /rash 206. Altase, ramipril ACE 207. Levaquin, levofloxacin fluoroquinolone bacterial infection 208. Keppra, levetiracetam antiepileptic seizure 209. Geodon, ziprasidone antipsychotic *** always take with food, similar to lurasidone *** 16/29 top 300 drugs, brand /generic /class /indication 210. Latuda, lurasidone antipsychotic *** always take with food, similar to ziprasidone *****211. Fanapt, iloperidone antipsychotic *****, same QT prolongation risk as ziprasidone ****212. Prolixin, flufenazine first generation antipsychotic if decanoate is the salt, 2 to 4 weeks 213. Humalog, insulin lispro, rDNA origin diabetes 214. Methadose, methadone pain / opioid withdrawal 215. Apidra, insulin glulisine diabetes 216. Lopid, gemfibrozil fibrate cholesterol / triglyceride *****, take 3 hours before breakfast and dinner *****, 217. Binicar, omezartan medoxamil 218. Furacet, butalbital / acetaminophen / caffeine migraine 219. Medrol, methylprednisolone steroid inflammation / rash / allergies 220. Pepside, famotidine H2 blocker GERD 221. Elunister, esopiclone sedative insomnia 222. Altracet, tramadol / acetaminophen pain 223. Trexaol, methotrexate daily for cancer weekly for Ra17 /29 top 300 drugs, brand / generic / class / indication 224. Januvia, sitagliptin DPP4 inhibitors diabetes 225. Cardura, doxazosin ±1 selective alpha blocker 226. Juvizinc, sitagliptin and simvastatin 227. Genume, sitagliptin and metformin 228. Minipress, prazosin ±1 selective alpha blocker BPH and HTN 229. Hitrin, trazosin ±1 selective alpha blocker 230. Binicar HCT, omezartan medoxamil / hydrochlorothiazide ARB and thiazide HTN 231. Actonel, risedronate bisphosphonate osteoporosis 232. Imita-E, sumatriptan migraine 233. Lomatil, dipenoxylate / atropine centrally active opioid diarrhea 234. Antivert, Dramamine, meclizine nausea 235. Cogentin, benztropine Parkinson's 236. Felden, piroxicam sed anti-inflammatory / pain 237. Cleocin, clindamycin oral lincosamide bacterial infection 238. Zavirox, acyclovir herpes, shingles chicken pox 18 /29 top 300 drugs, brand / generic / class / indication 239. Procardia, nifedipine DHP-CCB-HTN 240. Nifedical, nifedipine DHP-CCB-HTN 241. Adele, nifedipine DHP-CCB-HTN 242. Bumex, bumetanide diuretic HTN 243. Vesicare, salifenacin bladder relaxant overactive bladder 244. Acupril, quinapril ace HTN 245. Trivara, trifazole, Impris, levonorgestrel / ethinyl estradiol contraceptive 246. Avandia, rosiglitazone thiazolidinedione diabetes 247. Fnagan with codeine, promethazine / codeine cold medicine, opioid with HH1 antihistamine 248. Glucovance, glyceride / metformin sulf and biguanide diabetes 249. Novolin 70 / 30, insulin Novolin diabetes insulin 250. Mitaglip, glipizide / metformin sulf and biguanide diabetes 251. Tricycle, tricycle low, trisprintic, Trinessa, Nordstimate / ethinyl estradiol contraceptive 252. Zyprexa, olanzapine schizophrenia / antipsychotic 19 / 29 top 300 drugs, brand / generic / class / indication 253. Yasmin, Ocella, drospirenone / ethinyl estradiol birth control 254. Voltaren, diclofenac sodium oral, can also be gel for pain, NSAID anti-inflammatory and pain 255. Agrinox, dipyridamole / aspirin antiplatelet to prevent stroke 256. Boniva, ibandronate bisphosphonate osteoporosis 257. Compazin, prochlorperazine phenothiazine class antipsychotic, anti-nausea and anxiety 258. Compro, prochlorperazine phenothiazine class antipsychotic, anti-nausea and anxiety 259. Bactroban, mupirocin antibiotic for skin infections 260. Macrodantin, nitrofurantoin antibiotic for UTI 261. Furodentin, nitrofurantoin antibiotic for UTI 262. Macrobid, nitrofurantoin antibiotic for UTI 263. Latrisone, clotrimazole / betamethasin dipropionate steroid / antifungal. It can treat fungal infections 264. Flagyl, metronidazole antibiotic 265. Robaxin, methocarbamol muscle relaxant. It can treat muscle spasms and pain. 266 Tushnex, chlorpheniramine / hydrocodone antihistamine / narcotic and narcotic. It can treat cough 267. Ivista, raloxifene estrogen modulator osteoporosis 20 / 29 top 300 drugs, brand / generic / class / indication 268. Provigil, modafinil stimulant for narcolepsy 269. Nuvigil, armodafinil stimulant for narcolepsy 270. Carafate, sucralfate antacid. It can treat ulcers 271. Enables, derifenacin overactive bladder 272. Niaspan, niacin cholesterol medication and vitamin. It can treat high cholesterol and triglyceride levels as well as niacin deficiency. 273 Astelin, azilastin nasal itchy stuffy runny nose 274. Relafen, nabumtan said, anti-inflammatory. It can treat pain and arthritis. 275 Valter-E, valacyclovir herpes, shingles, chickenpox 276. Armothyroid, thyroid, desiccated, T3 and T4 hypothyroid 277. Zafran, ondansetron nausea / vomiting 278. Acifex, rabeprazole PPI GERD 279. Sinequan, docupin TCA anxiety / depression 280. Theocron, Theo24, theophylline anhydrous asthma, emphysema COPD 281. Chantix, varenicline tartrate smoking cessation 282. Timoptic, timolol maleate ophthalmic non-selective BB 283. Bitopic, betaxolol ophthalmic selective BB21/29 top 300 drugs, brand / generic / class / indication 284. Ocuprus, cartilol ophthalmic selective BB285. Omnisf, cefdinir antibiotic 286. Levemir, insulin detemir diabetes 287. Pristic, desvenlafaxine antidepressant 288. Biota, exenatide GLP-1 agonist diabetes 289. Lovasa, omega-3 acid ethyl esters triglyceride 290. Mycardis, telmisartan ARB-HTN 291. Zalatan, latanoprost glaucoma 292. Stratra, atomoxetine SNRI-ADHD 293. Vtids, PenVK, Veselin, penicillin V potassium 294. PenVK, penicillin V potassium 295. Veselin, penicillin V potassium 296. Atripla, efavirenz, imtricitabine, tenofovir fumarate HIV 297. Plaquenil, hydroxychloroquine sulfate malaria in third world countries, RA and lupus in first world 298. Zoroxolin, metalazone thiazide diuretic 299. Thalidan, chlorthalidone thiazide diuretic 300. Prisca, finasteride BPH 301. Mitacin AC, codeine / guaifenesin cough 302. Robitussin AC, codeine / guaifenesin cough 22 / 29 top 300 drugs, brand / generic / class / indication 303. Minopril, Fosinopril ACEIHTN and HF 304. Prempro, estrogen, conjugated, / medroxyprogesterone acetate estrogen replacement therapy for hot flushes caused by menopause 305. Patanol, olopatadine ophthalmic eye allergic conjunctivitis 306. Pataday, olopatadine ophthalmic eye allergic conjunctivitis 307. Mavic, trandelapril ACEHTN 308. Vival. Estradiol topical hormone replacement 309. Luminol, phenobarbital beribwate sedative 310. Sulfotan, phenobarbital beribwate sedative 311. Vicaprofen, hydrocodone / ibuprofen opioid pain 312. Orthocycle, Sprintic, Norgestimate / ethinyl estradiol contraceptive 313. Avalide, irbesartan / hydrochlorothiazide 314. Hyzar, losartan / hydrochlorothiazide ARB and HCTC for HTN 315. Plendil, felidipine 316. Yaz, drospirenone / ethinyl estradiol contraceptive 317. Pulmicort, budesonide inhalation steroid asthma 318. Travatan Z, travoprost glaucoma 319. Zysel, levetiracetam antihistamine for allergy 23 / 29 top 300 drugs, brand / generic / class / indication 320. Nasacort AQ, triamaquinolone acetonide intranasal allergy symptoms 321. Lostrin FE, microgestin FE, Junal FE, norethindrone / ethinyl estradiol / ferrous fumarate contraceptive 322. Adipex B, phentermine appetite suppression for obesity 323. Ionamin, Phentermine appetite suppression for obesity 324. Cordarin, amiodarin potassium channel blocker antiarrhythmic 325. Pacerone, amiodarin potassium channel blocker antiarrhythmic 326. Nizoral, ketoconazole antifungal 327. Avapro, irbesartan 328. Pamela, nortriptyline SNRI for depression 329. Arimidex, anastrozole estrogen for cancer 330. Avalox, moxifloxacin fluoroquinolone 331. Tamiflu, oseltamivir flu vaccine 332. Viagra, sildenafil citrate ed 333. Aprizoline, hydralazine HTN 334. Vivance, lisdexamfetamine dimesylate ADHD 335. Alphagon P, brimonidine tartrate glaucoma. Also it can treat facial redness caused by rosacea in its topical form 336. Lidex, fluoquinonide topical steroid. It can treat many skin disorders. It can also relieve pain, itching, and swelling of the skin. 24/29 top 300 drugs, brand /generic /class /indication 337. Nystatin oral. Nystatin oral. This medication is used to treat fungal infections of the mouth. 338 Minokin, minocycline tetracycline antibiotic 339. Levsin, Levbid, Levsin X, Hyosoyamine gut spasmodic for IBS 340. Levbid, Hyosoyamine gut spasmodic for IBS 341. Levsin X, Hyosoyamine gut spasmodic for IBS 342. Cialis, tadalafil 343. Cosept, dorsalamide /timolol maleate /non-selective BB 344. Pyridium, phenazopyride in urinary tract pain 345. Peridex, chlorhexidine gluconate. Chlorhexidine is an antibacterial used as an antiseptic and for other applications 346. Periogod, chlorhexidine gluconate. Chlorhexidine is an antibacterial used as an antiseptic and for other applications 347. Lumagan, bimatoprost antiglaucoma. It can reduce pressure inside the eye in its eye drops form. As an eyelash solution, it can help eyelashes grow. 348 Nuvaring, etonogestrel /ethinyl estradiol vaginal contraceptive 349. Prometrium, progesterone oral menopause 350. Lamizil, tarbinafine antifungal 351. Vigamox, moxifloxacin ophthalmic bacterial conjunctivitis 352. Sumicin, tetracycline antibiotic 353. Panmicin, tetracycline antibiotic 354. Tamuvate, clobetasol propionate topical steroid itching redness 25/29 top 300 drugs, brand /generic /class /indication 355. Pruvera, medroxyprogesterone acetate contraceptive or endometrial pain 356. Ofral, low /ofral, ogestrel, Crisel, Norgestrel with ethinyl estradiol contraceptive 357. Bioxin, clarithromycin macrolide antibiotic 358. Dimadex, torsemide diuretic edema or HTN 359. Indocin, indomethacin said, anti-inflammatory, it can treat pain. 360 Atacand, candesartan silex-ethyl ARB for HTN 361. Allegrity, fexufenadine / pseudopedrin allergy and congestion 362. Normodine, labetalol non-selective BBHTN 363. Trandate, labetalol non-selective BBHTN 364. Restasis, cyclosporine emulsion ophthalmic immunosuppressive agent used to treat chronic dry eye caused from inflammation 365. Mycardis HCT, telmisartan / hydrochlorothiazide ARB plus thiazide for HTN 366. Tenoritic, atenolol with chlorthalidone cardioselective BB plus diuretic 367. Mycolog2, nystatin / triamaquinolone acetonide fungal skin infection and inflammation caused by it 368. Disogen, Apri, orthocept, disogestrel with ethinyl estradiol contraceptive 369. Oriprid, prednisolone sodium phosphate inflammation, multiple sclerosis, and arthritis. 370 Zyma, gatiflocasin ophthalmic bacterial conjunctivitis 371. Levitra, vardenafil ed 26 / 29 top 300 drugs, brand / generic / class / indication 372. Staxin, vardenafil ed 373. Suboxone, buprenorphine / naloxone opioid withdrawal 374. Decadron, dexamethasone oral inflammation, allergic reactions, and flare-ups of ulcerative colitis. 375 Veramist, fluticasone furoate nasal allergy, congestion, sneezing, itching 376. Ciprodex, ciprofloxacin / dexamethasone treat outer ear infections 377. Focalin, dexmethylphenidate 378. Latensin HCT, benazepril / hydrochlorothiazidase and thiazide for HTN 379. Elicon, mometazone furoate topical eczema, psoriasis, allergies, and rash 380. Clarinex, disloratadine antihistamine. It can treat or prevent hives, allergy symptoms 381. Nolvadex, tamoxifen citrate 382. Duomb, ipratropium bromide with albuterol sulfate solution bronchodilator. It can treat COPD. 383 Conchita, methylphenidate 384. Oxy-IR, oxycodone IR opioid pain 385. Roxicodone, oxycodone IR opioid pain 386. Miralax, polyethylene glycol 3350, NF osmotic laxative 387. Glycolax, polyethylene glycol 3350, NF osmotic laxative 388. Zyac, bisoprolol / hydrochlorothiazide selective BB / thiazide diuretic HTN 27 / 29 top 300 drugs, brand / generic / class / indication 389. Lostrin 24-FE, norethindrone acetate, ethinyl estradiol, ferrous fumarate contraceptive 390. Colchris, colchicine 391. Avodat, dutasteride BPH 392. Ceftin, sfloxime oral CEF antiarbic 393. Ales, Avion, levonorgestrel with ethinyl estradiol contraceptive 394. Mercet, Cariva, disogestrel with ethinyl estradiol contraceptive 395. Necon 1/35, orthonovum 1/35, norethindrone and ethinyl estradiol contraceptive 396. Prevnar, pneumococcal vaccine 397. Lupron, Luprolide GnRH agonist prostate cancer 398. Zoladex, Goserelin GnRH agonist prostate cancer 399. Zytiga, abiraterone androgen biosynthesis inhibitors, prostate cancer 400. Casodex, bicalutamide first generation anti-androgen prostate cancer 401. Firmagon, Degarelix GnRH antagonist, prostate cancer 402. Rainexar, ranolazine add-on therapy for stable angina, reduce oxygen demand, reduce number of attacks, 403. Nimotarp, nimodipine non-DHPCCB hemorrhagic stroke 404. Cardin, nicardipine CCB 28/29 top 300 drugs. Brand /generic /class /indication for hypertensive 3 in ischemic stroke patient, labetalol is other option, 405. Osmitrol, mannitol hemorrhagic stroke 406. Invokana, canagliflozin SGLT2 diabetes 407. Farxiga, dapagliflozin SGLT2 diabetes 408. Jardiance, empagliflozin SGLT2 diabetes 409. Precose, acarbose alpha glucosidase inhibitor diabetes **** no meal, no drugs **** 410. Glyze, miglytal alpha glucosidase inhibitor diabetes **** no meal, no drugs *** 411. Invirase, scowinavimesylate not ***** scowinavi soft gel capsule **** 29/29.
Purpose of these episodes not at all for advice or medical suggestions. These are aimed to provide support to peer pharmacists in training in educational and intellectually stimulating ways. Again, these are not at all for medical advice or medical suggestions. Please see your local board and state-certified health professional. The views of this podcast represent those of my guests and I.
Thanks for listening to the podcast series The New Student Pharmacist, where we discuss chemistry and pharmacy, as well as leaders in pharmacy careers, community, and chemistry and pharmacy research. We encourage you to support the work we are doing and follow us on Spotify and Apple Podcasts by subscribing for free. We are so glad that you were able to tune in today. Note, the views on the podcast represent those of my guest, and I take care and all the best.
You are very important, especially to us here at the New Chemist podcasting group. You listening in is significant.
Vous êtes très important, surtout pour nous ici au New Chemist Podcasting Group. Votre écoute est significative.
Usted es muy importante, especialmente para nosotros aquí en The New Chemist Podcasting Group. Usted escuchando, es significativo.
Você é muito importante. Especialmente para nós do The New Chemist Podcasting Group. Você ouvindo, é significativo.
Είστε πολύ σημαντικοί, ειδικά για εμάς εδώ στο The New Chemist Podcasting Group. Το να ακούς είναι σημαντικό.
Sie sind sehr wichtig, besonders für uns hier bei The New Chemist Podcasting Group. Es ist wichtig, dass du zuhörst.
Je bent erg belangrijk, vooral voor ons hier bij The New Chemist Podcasting Group. Dat je meeluistert, is veelbetekenend.
You are very important, especially to us here at the New Chemist Podcasting Group. You listening in is significant.